That's working. Just streaming. Okay. Always stays. Yeah, I think so. We can get started. Ajit has a mic. You can use this mic. Is there a mic? I think this one is also a mic. Yeah, I think. Yes.
Good morning, everybody, and welcome to this workshop on data science and astronomy. My name is Ashish Mahathur. I'm from Caltech and also an active faculty here. I'm one of the organizers, but Surud has been doing all the organizing. He's here. Shreyash Tendulkar is here, Yogesh is here, and Shushmita Adhikari is one of the other organizers. And so what we'll have over the next 3 half days is the first day we'll have a lot of introductory talks on different aspects of data science, not particularly focused on astronomy, but more about the techniques and libraries, etc. Tomorrow there will be many use cases specifically related to astronomy. But the hope is that today's broad introduction gives you an idea how it could also be used in other fields. And on the third day, we'll have what we are calling a hackathon, but it's not just a hackathon in the usual sense of the word. That it is not something that will sit there for 2 hours and just keep on programming and finishing something. But there'll be a lot of ideation, trying to come up with different projects, something that can even take longer. So this will be an initiation process in some sense if you want to get involved in astronomy data sets, etc. So it can be a partnership over a longer term. So there are many institutes here in Pune, NCRA, IUCAA, ISER, and many colleges. So this should be a welcome opportunity for students to connect with various others who have been working in data science. So we will also encourage you to bring data sets, etc. And you'll get more information about all these things. So let's start. We'll initiate this with an introduction to data science and astronomy and classical machine learning. Professor Ajit Kemavi. Ajit was the former director of IUCAA, also my PhD advisor, so I've learned a lot from him about many of these things. And let's start it off.
So, good morning. I'm a little bit confused about what I'm going to be talking today. So, because my friends who are organizing it, they said they will talk on an introductory thing. And then after some time, they reduced the length of the talk to 25%. And the day before yesterday, they said, no, it should go back to 100%. And it went on like that. And, also, they asked me to do virtually everything under the sun or under the sky. So what I've done is that that one specific thing which I was asked to not do is to refer to any of the latest developments. Okay, so that fits in well because many of you might be wondering why somebody like me is doing this AI business, okay, which is all for young people. But then I work with a lot of young people and take sustenance from them. And the young include probably the oldest of the young people is Ashish, but there are several others in the hall that I work with. And also, what I'm going to do is to talk about all matters like machine learning and even deep learning. 5 or 6 years ago, I heard about deep learning accidentally. It was very new at that time. But now there are many other techniques which are becoming more fashionable. You'll hear about those techniques during the course of this workshop. I'm going to talk about machine learning. And other thing that I'm asked to do is to give examples of the problem from starting from the old techniques to how the things have changed over a period of time. So that is the brief that I have accepted, and I'm going to do that. I was also asked to introduce astronomical data, but that became impossible because of the time which is available. So what I'll do is that I'll just refer to the astronomical data as it considered examples. I wanted to include examples of biology, but again, that is also not possible, but we'll see maybe over the next few days we can have discussion. A very important thing for all of you and for us too, on this other side of the table, is that these events are not considered to be one-off events. Okay, meaning that you just go to listen, learn a little bit and go away. What we are looking for is people who will be interested in taking this forward, learning, and doing projects also. And so right now, many of the people in the hall are, I mean, each one of them is independently like a Christmas tree. Okay, meaning that there are lots of projects hanging there, and so you can just pluck off whatever you like and work on it. And there are many immediate projects, and some of which I'll refer to as I go along, but please do remember that. But what we are interested in is people who know a little bit already, meaning that we don't want to hold your hand and teach you machine learning, but just a little bit, and then who are adventurous and who are willing to be original. But these projects always lead to research publications and products, all kinds of things. Okay, so they will leave a legacy behind. Please keep that in mind. And so this is AI applied to and machine learning with applications to astronomy. So then I've also put the Pune Knowledge Cluster. Some of you have heard about it. And there too we have the Pune Knowledge Cluster. Big data and AI is one of the verticals on which we are working, and that's only increasing as we go on. Right, so now machine learning and deep learning. I forgot to include one slide here, which says that which shows what are the relationship of all these. These names are all, as you already may be aware, they are not very hard and fast. Okay, so to my mind, there is this thing of artificial intelligence, which is AI, and machine learning is a part of it. Now, machine learning has everything like artificial neural networks and so many other things that are in it, and deep learning is also a part of it. And so then, so that is how the hierarchy goes. But you see that sometimes it gets inverted. Sometimes we talk of AI and ML. That has become in the popular parlance, because AI now is talked about by absolutely everybody. And they always talk about AI and ML as if these are two separate things. They are not. Okay, so so in general learning schema, I wanted to change this slide. I've been using it for some time, but I did not have the time to do it. So when we said we'll talk about learning, machine learning, now what does it actually involve? So you see that we are trying to do carrying out a task, like say classification. Okay, so we want to be able to recognize different animals from each other given the images of these animals. And so then what you require is a learning algorithm. So there's something which you're trying to teach something to do this. Okay, and then you've got the input data. The input data can consist of almost anything at all. For us as astronomers, it can be images and or spectra. It could be sights, it could be sounds, whatever. Okay, the input data. Okay, and then using the input data, the learning algorithm, so you get a trained model. And so it will learn all that you want it to. So how do I know whether my trained model is good or not? For that, I require a test it. Meaning that let us suppose that I learn to distinguish between cats and dogs. Then I use lots of images for that, and then I'll have an independent set which has not been used in the training, and then I test my trained model against that set. Okay, then I will say that look, I mean 99% accuracy has been achieved. Right, so then accuracy of recall, meaning that if I tell you that 1,000 objects which I'm giving you are galaxies of a particular kind, the question is how many of those really are galaxies of that kind? Okay, so this requires you to define something which is called accuracy. Okay, then other one is that I start with a set of 1,000 known galaxies and mix them with other objects and ask your trained model to pick those 1,000 galaxies. And you may be successful only with 8 or 900. If you do it for 900, it means that your completeness is 90%. And so you want to increase the accuracy and you want to increase the completeness also. Okay, accuracy 100%, completeness 100%. Okay, that means that your training is completely faulty, your data is not enough. And so you have to be circumspect about these things. And so then, what do you do with this? A trained model is that you need a usable product. Okay, meaning that I make a catalog of galaxies. Okay, or I give you a thing where you can recognize faces. So you need a usable product at the end of it. Okay, this is not an academic instance. Okay, so then there are two important divisions here. One is that data with labels and data with labels and data without labels. And so meaning that when I'm dealing with known objects, I want to classify known objects. Okay, then I'll put a label on each one of them. Okay, but on the other hand, it's just a mix of objects which I want to try to classify. Okay, then and I don't know how many classes are there. Then I can ask the system to decide to define the classes by itself. Okay, so that will be unsupervised learning. And then you will find that we can also do a mixture of supervised and unsupervised. Okay, then you see that I just separated out these two because there are only two things I'm going to consider is machine learning and deep learning. The important difference between them is that because of the limitations of machine learning, okay, I'll come to what those limitations are, okay, then you need to give it typically extracted features. Okay, so meaning that if I'm trying to classify faces using machine learning, I'll divide that into a small number of pixels and give that. Okay, or if I want to distinguish between people who are young, people who are old, people, then the weight of the person, the height of the person, and things like that will become input data. Right, and then in deep learning, you progress on to the modern technology because of first of all, the development of the algorithms, a deeper understanding of what goes into the classification, and second, what people like me call compute power, but what the AI experts call compute. Okay, so compute for me the verb, but they use it as a noun. So we have got a lot of compute. So Microsoft gave $13 billion to OpenAI. So what do you do with the $13 billion? How many palaces can I build? How many people can I hire? So no, it is all for the compute. Okay, meaning for the computing power, which is absolutely at the basis of everything that we need to do. And so then I find this example very, very useful, is that the binary classification. So the problem here is the following, is that there are these points. Okay, so there's the x-axis, x1 and x2 axis, and these are just the coordinates. And this is a distribution of points. Now, what I want to do is to learn, to train a model, okay, in such a way that if I give you any coordinates x1 and x2, you should be able to tell, you must have a single criterion by which you can say whether it belongs to the red group or the blue group. Now the colors and the shapes are consistent for the scene. The only reality here, the only input data are the two coordinates. Okay, so how would you do that? And the simplest way would be to just draw a line. And so this line clearly divides out these points into two different classes. Now, having drawn this line, you would say that how do you define the line? Is that you've got a normal to the line, right? And then this would be the equation of the line. W dot x is equal to 0. Where W is this vector which tells you how the line is oriented. And so then on this W dot x is equal to 0, And it's very easy to show that in this region, W dot X plus B is greater than 0, and in this region it is less than 0. So if you know what is the vector W, okay, so which means that if you know the slope and intercept of the line, just simple coordinate geometry, then you'll be able to say that if W dot X plus B is greater than 0, then you will belong to one group, otherwise you belong to the other. And so therefore it's very simple. We got it right. Now, now the question is, how would you train a perceptron to do it? Okay, so I won't define what's a perceptron. You know, you can make an analogy with neurons and so on. But what happens here is that there is a machine. It could be just a software thing or it could be a hardware thing. And I'll show you some pictures very quickly. And you input coordinates. And now these coordinates, you don't have to restrict yourself to just 2 coordinates. And you can be a 11-dimension thing, which is important to particle physicists or whatever. Okay, so you've got all the dimensions. And then what happens is that you build this circuit or this program in such a way that you give it all these things. And then it can attach weights. It will multiply x1 by w1, x2 by w2, sum it together, and it has got an activation function. Okay, which means that if it is greater than 0, it is set as 1. If it is less than 0, it is minus 1. Right? So you do that. Okay, then what happens is that, sorry, minus 1. So how to write this program is a different matter. Right? So then what you will do is actually you will take known points which are here. You will start with some arbitrary weights, W1, W2, W3. Okay, then you will take these known points and you say that for this coordinate, let us say that this is 11.2 and 13.5 or whatever, we say that it is 1. Like that. Okay, so that is what is called supervised learning. These points are already known. Now, how do you actually do the analysis? How do you train the system? Is that you start with arbitrary values of W. Okay, reasonable, you can put all of them to 0, all of them to 1 or whatever. Okay, and this signum says that if W dot X is greater than 0, it's 1 or it's minus 1. Then you set up an error function. Okay, where for each point they use a training. This is a true value, meaning it is 1 or minus 1. And this one is the value we'll get by passing it through the machine. Right, and then what we will do now is a sum of squares, because otherwise the pluses and minuses we cancel each other. And now I minimize E. And so, because this is the error function, and the best fit is obtained by minimizing E. And simply by taking derivatives with respect to W. And what is eta? You choose a small value there, it tells you how fast or how slow you can make the changes. Right? So now you see when you do this, sorry. Yeah. When you do this, then when you minimize it, it's a trained machine. Then you take new points and test it, and so on, as I already mentioned. Okay. So you see that now this seems like a very, very simple thing to you. As I explained it, I'm sure that all of you will be able to write this code. But you must understand that this was developed over various decades. Because there's a person called Rosenblatt, but there are also many other people. And he developed the algorithm for this, for linearly subredded systems. Okay, and then he actually built a hardware which could do that. Okay, then what happened was that people wrote a book in which they said that, look, this for the single perceptron, because there's only one perceptron here, this applies, it applies only to linear systems, and it cannot apply to non-linear systems. I'll tell you what is a non-linear system as I go along. Okay, and then, and therefore, people start actually working on that. Okay, so that people could not get grants, and the whole thing got delayed by a couple of decades. Okay, Rosenblatt, of course, died before the new developments which came into the picture. Now, over this period of time, you know that each one of these steps is also supported by a great deal of research, and some of which can be traced back to very old research went on independent of machine learning. And then you construct a series of theorems. Okay, now you see what happens here is that if there exists a solution, meaning that when I show you those two things, you know that there exists a solution because you draw a line. But many times the distribution of points can be difficult to comprehend, and you don't know whether there exists a linear separability. But what this theorem tells you that if there's an exact solution, then the training data is linearly separable. The perceptron training algorithm is guaranteed to find an exact solution in a finite number of steps. Okay, so which means that you can do it. Okay, then second, the number of steps needed for conversion can be substantial. Okay, and then you see the problem here. I find this very interesting. Until convergence is obtained, you're not sure you can do it or not. So just imagine that you have got all this computing power, you go on, you do it. Nobody knows. So clearly, no, people are not going to give you a grant, okay, to do this kind of thing. Okay. Then for data sets which are not linearly separable, the perceptron learning algorithm will never converge. And so if it doesn't converge, you don't know whether you wait until tomorrow afternoon it will converge or not. If it is not separable, you cannot make any hard and fast statements. But understand that this is just the beginning. I mean, if it stopped here, then there will be there's nothing more that you could do about it. Right? So now this is, we got a Mark 1 perceptron. I mean, I started reading about this only yesterday evening. Okay, so I found it so interesting that I'm going to study it a little bit and develop the whole thing into something which will be useful to people. So this is a perceptron, Mark 1 perceptron, and there are all these connections here. And this is Rosenblatt. And just look at this second, how complicated it is. And what are these things? These things are, there's a hardware which supplies the weights. And then some of these are storage devices. So they can just store one number. So you see that it was all very difficult to do. And people still persevered and got the whole machinery going. All right. Now we'll pass on to more complex problems, and which tell you how beautiful the whole thing is. Now look at this problem here. Now here, you've got these two sets of points which I want to separate. And when I want to separate them, I clearly cannot do that with a straight. Okay, so what I want is a surface. Now, if I asked you to solve this problem in the classic way, what would you do? Is that, first of all, you will have to consider a curve, a model curve, okay, which you pass through it. And then what you'll do is that you'll again set an error function, and then you'll change the weights, or you'll change, you'll just minimize the error function. I'm not even talking about AI. I'm just talking about your usual curve fitting. Okay, you do that. But the curve required is very complex. I can do far more complex things where you wouldn't even know how to start thinking of what you call a test curve. Right? So you need to really learn things ab initio without appealing to your previous experience. Right? So what happens there? Now it turns out that with a single perceptron, you cannot really do anything which is non-linear. So you require more than one perceptron. Now the perceptron now gets divided into three different groups. So you see that here, let us say that it's a 4-dimensional space. So there are 4 inputs because I have given you, if I give you 4 coordinates for 2-dimensional space, we'll have 4 coordinates. So you have enough number of input devices. And each one of them is connected to this layer, which is known as a hidden layer. It's called a hidden layer because it is neither a part of the input nor a part of the output. Okay, so you've got a hidden layer, and this is the output. So in our simple straight line case, what you'll be doing is that there are just 2 inputs, x1 and x2, and we have just one perceptron in KU. Now, but I can say that I just want to know which group it belongs to. So the output can be 1 or 0, or the output can be 1 or -1. Now you've got this hidden layer. Now the thing is that there are 2 phrases that you'll come across. One is a feed-forward network. Okay, so feed-forward network, meaning that you see that here are the inputs coming in, each one of them is connected to every single one of the hidden nodes, and each one of those is connected to the output. So you're going forward, forward, forward. So now there is nothing sacred about this. This is called a fully connected feed-forward network. You can omit some connections and you can take something that is going back. Every single variation that you can think of has been tracked. Okay, so by the time you do it this morning, in the afternoon, somebody will come out with something else because it's an extremely fast developing field. And of course, all these things happened about 20 years ago. That's why we've got a feed-forward network. And then we've got something called backpropagation. Okay, meaning that you remember how we minimized our function. What we did was that we took those derivatives because that's called steepest descent. And we took derivatives and then we changed Wi and minimized E. But here, because of the many different layers which can be there, that requires very careful taking of derivatives starting from here and going back there. So it is called backpropagation. It is nothing really, it is just what chain rule of calculus. So how do you do that? Now, with this, what can you do? So let's go forward here. And one very important thing is that because we want a non-linear surface, non-linearity has to be introduced. What did we do? We just took w dot x plus b. Okay, it was inherently linear. So what you have to do is that the output of each node has to be made non-linear. Now it turns out that you can have very simple kinds of non-linearity, meaning that this is known as a sigmoid function. And that the sigmoid function is defined here. And you see that here infinity goes to 1 and then it goes to minus 1. So a large variation in the parameters is quashed with the sigmoid function. And other way you can introduce the non-linearity is this absurdly simple function. So which is 0 here, the output can be 0 and up to some point and then it gets to a straight line. So the non-linearity entirely comes out of this particular point. And so these are the kind of non-linearities that we use. So when these are used at a what's called artificial neural network is set up. This was done by a postdoc called Kaushal many years ago. Okay, so he used a nonlinear function, is a tan hyperbole. You know how tan hyperbole is defined, so it's that one. And then he minimized the thing and then he got this surface. So you must understand, so now if you give the machine the trained circuit, x1 and x2, then it will tell you immediately whether it belongs to this group or that group. But what is very important for you to understand as a matter of principle is that neither the equation of this particular line was no point required. And you don't even know the equation after the job is done. And so it is a completely different approach from the classical approach of starting with a model curve. So why have you drawn this curve? It is purely to guide the eye. Okay, and then also, how did he draw the curve? He drew the curve so that you get the best result. Okay, meaning that the error function becomes really minimum for this curve. That's all. And so now you can imagine it can be a very complex system. It can be any number of dimensions. All sorts of things are possible. And so the question again here. So you get what is known as a multi-layer neural network. So we started with one layer of hidden layer. But you see that here you've got two hidden layers. So you can have any number of hidden layers like that. Okay, so how do you know whether this network should be a one layer or two layer? Now you will come across this kind of question in every aspect of artificial intelligence. Okay, so there are guiding theorems which no one knows anything about. Okay, so what happens is that you generally go by experience. So everything depends upon the problem that you want to do. So you know that you can go into another software systems about which since I'm really sorry, that reminds me, you gave me a certain number of slides to be included. I totally forgot. Yeah. Okay, so we can use them later. We totally forgot. Yeah, so there are these software systems which you can learn to operate in about 1 hour's time. And then you can start applying it and apply for a job with it. The problem is that it requires a very great deal of experience, okay, to see whether what you're doing is right and whether the answers that you're getting right. So it may not be so hard to get the exact answer when I'm trying to classify galaxies. But just imagine that I'm using it to recognize people who are walking into an underground station, or I'm guiding a fighter plane using this technology. Okay, then the margin of error is extremely small. Okay, you can straight away finish off the whole system. So I tell you what happens when I got so-called driverless cars, right? They send them out and then 4 days is okay, the 5th day you make a bad accident. Right? So therefore, you need to know when should I have 1 year, when I should 2 years, etc. One simple thing is that there is a theorem which tells you that every bounded continuous function. Okay, meaning you know what is bounded and continuous? Let's say a nice function that you know about. Okay, can be approximated with arbitrarily small error. Okay, by a network with just one hidden layer of units. Okay, so this is a very important statement that I got the input nodes and I got the output and I got one hidden layer. Okay, so one hidden layer is completely enough to have this kind of a function. Continue. What do we mean by a function here? You see any distribution of points, anything that where you're putting in the unknown thing and you're getting an output. That by definition is a function. Right, so the network uses a sigmoid unit, hidden layer and unthresholded linear units. Then any function, this is a continuous function. Now here any function whatsoever can be approximated to arbitrary accuracy by network of two hidden layers. Okay. Now look at this very helpful statement. The number of units needed in each layer is not known in general. Right? So that is what requires an expert. If everything was defined, then you don't have to attend this kind of thing. Right? So you see that 1 layer will do in most cases. In more complicated cases, you need 2 layers. But you can find people use 3 layers, 4 layers. So why don't they use 3 layers and 4 layers? That is simply because they want to make life easier. They want a convergence faster. So you see that the thing here is that yeah, I mean, yeah. This one is forward, right? I think that pretty well. This one is forward, this is backward. Yeah. Okay. So what was I saying? It was
Let's move to the next slide.
yeah. You see each one of them. You see that each connection here is associated with a weight. Okay, we had x1 w1 plus x2 w2. So here, for example, if you are connecting node number 2 to node number say 4 here, 5 here, then you'll have weight w2 5. Okay, so the number of weights can keep going up, and gradually it becomes uncontrollable because the computation goes up, the complexity of the function goes up, and you can't do it. So then it turns out that by splitting it up into one very large layer, you can have 3 layers because you see each layer will look like x1, x2, x1, x2, x3 terms like. And so you can optimize your function to this one. And so, so one last thing I want to say here is that this theorem, for example, it is to a person called Kolmogorov. Again, he had nothing to do with AI. He was on the turn of the 20th century and worked for a few decades after that, and he was a very, very deep person. Okay, so all kinds of, for example, the Kolmogorov split of test. Okay, so you want to compare 2 functions, you have got that. But he has contributed to every area of knowledge, what you call applied mathematics. All right. Okay, so now, so what I'm saying is that you can do anything you like with machine learning, with artificial neural networks of the kind that I described. but things become more and more complicated. And so let us look at President Obama. Okay, so let's say that you want to learn to recognize his face. Now, in the old days, if you read this beautiful book on machine learning by Mitchell, it's a very beautiful book. I strongly recommend that you read it. It's a very old book, and so there he actually talks about classifying the face using this. But if you look at the resolution, it can be very appalling. Well, what is the problem? That the simple thing that you take with your cell phones, you have many megapixels, 10 megapixels, 15 megapixels. So which means that a face like this taken with a cell phone would have say 15 billion pixels. And I want to be able to recognize these faces. So which means that your input will be 15 billion. And then you need all those layers. And then you have the outputs. And so clearly it is going to be a really what you call humongous task. I mean, it will be practical undoing. So then what do you do? Okay, you say that let me reduce the resolution. But this can become like throwing the baby out with the bathwater. Okay, so I'm doing this, I'm doing a lot of pixelization, and then with that pixelization, I'm losing information. So you may find that if you do this hard enough, then you'll find you can't say with Obama or with Trump. And so then you really then don't want to get into a situation like that. So, so what you do is that you want to now invent new techniques. Right? So, so then, therefore, you go to deep learning. Now, what deep learning does? You see that there is this very beautiful, very subtle review of deep learning by Lincoln, Benguiu, and Hinton. And these are all people who have, some of them have got this awards, and there are all people who have made very fundamental contributions and review in Nature. So please do take a look at it. I mean, the PDFs are available all over the place. Okay, so so here, what does deep learning do? The artificial neural networks, ANNs work on features extracted from the data. Okay, so I'll again explain that later. Then, example, the domain expertise and careful engineering are required. Which feature should I use? Okay, so that can become quite difficult to define. Because we are not talking of the simplest exponential coordinates, we are talking of real life problems. But deep learning networks work directly on the data, identifying useful features from the data, and downsizing. Downsizing it meaning you start with a large image and then you're going to pick up only the more important pixels from it. Okay, such networks can therefore address very complex data, which should be intractable for conventional networks. And so, so the very sketchy thing about these deep learning networks. And so you've got these layers there. And what happens in these layers? Well, you see, I would say that qualitatively, you will get more rigorous thing later. Is that when I'm looking at one of you, looking at your face, my brain is not dividing it out into pixels. So one thing I forgot to mention, if you really divide it into pixels and try to use an ANN, then one important thing is that you don't have to give the pixels in that order. I don't understand it like this. I can scramble the pixels and use them. And so which means that you are not using very, very important information. Because when I'm looking at your faces, okay, I'm going by the pattern of your hair, by your eyebrows, by your nose, by your lips. And all those lead to almost instant recognition. Okay, so the relative placement of the pixels and things like brightness, texture, everything is very important. And so once you recognize this, then how do you implement? So that can be implemented by having a series of what are known as filters. Okay, so meaning that just imagine that I take a horizontal filter, it's just a horizontal slit and I slide it across the face. So it is going to change when you pass the eyebrows. Well, because it will change in intensity, there will change in color. But it is not going to change to the vertical thing. Then I take a vertical slit, then I take a circular slit. And the process by which you are passing the slit is what is known as convolution. Meaning that I won't define a mathematical operation, but you're taking a function which defines my face. It will define my intensity, let us say. The intensity in 3, 4, 5 different colors so that you get all the details of my face. And then you convolve it with a filter. And that filter can be, for example, 1, 1, 1, and everything else is 0. A small rectangle. And then you carry out this process which is known as convolution. So what the system does here is that it has got a series of these filters. And so which is looking for edges, curves, all sorts of things. Okay, then you see that even things like textures are there. And then what happens is that each following application of these filters, and when do you do what is a little bit complicated, but you learn as you go along. And when you're after the filters, then you can do what is known as downsizing. Okay, so where what happens is that I take a 3x3 array, 4x4 array, etc., and then I pick up from that the largest bits. Okay, or I can take a mean and pick it up, or I can take a median and pick it up. And so instead of having 9 pixels, I'm reducing it by a factor of 1/9. So first, you have looked at the features by having this filter, then you go to 1/9. Now, who decides which filters are going to be? The system defines. Okay, so that is the beauty of it. Okay, because if you start defining filters, then you are engineering, which you are not allowed to do. Then so you tell the system that have 3x3 filters or 4x4 filters and have 15 of them or 20 of them or 75 of them. And so then the system does what it wants. Right? So, so you see that when this has been done, then what happens is that this particular deep learning network has been trained to distinguish between a car, truck, airplane, ship, and a horse. So once it is trained, and once I give this car to it, okay, then you'll find that it doesn't give an absolute value. You don't say it's a car. It will say it's a car with certain probability, it's a ship with a certain probability, and so forth. Okay, and then there are ways in which these probabilities can be derived. Okay, and then so you see that clearly the highest probability here is a car. Okay, so now the question is whether it tells you that it is a 99% probability that it's a car, then it will be quite easy for you to accept it. But what happens if the 80% probability that it's a car? Okay, then do you accept it or not? And then it's up to you. And so because if I'm preparing a catalog of galaxies, and then I got 99% probabilities for the identity of the galaxies, then if I take 10,000 of them and work on them, then only 100 of them will be wrong. Okay, but with 80% probability, then many more will be wrong. So you have to make a judgment as to what is acceptable. But this gives you some kind of a quantitative. Okay, so now if you go to what is called the AlexNet, and so you learn more about this, which gives you a standard architecture. Okay, so then you see that there are so many of these convolution networks, and then this is the kind of nonlinear function which are being used. And these are pooling layers. Pooling layers means that there are the downsizing layers, and then there is a particular thing. And what is most important is that by the time you come to this particular stage, the data has been downsized very significantly, and it is possible for you to have an ANN. Okay, and the ANN which carries out the classification. You couldn't do that to the original data because there's so much data, and so now you have brought it to that level. Right. How much time more? 10 more minutes.
I have a question.
Yes.
In the CNN, do you get saturation after, I mean, you can define how many filters you want to use.
Yes.
But increasing number of filters after a while wouldn't matter.
Yes. Yeah. Okay, so there are two things there. Let me go on for 5-10 minutes and I'll come to 10 minutes and I'll come back. Okay, so you see that here I have made a thing about the different things of ANNs, random forest and decision trees, support vector machines. So I've been working with my young colleagues for a long time, and then there's a lot of problems. So you see there's an example how to distinguish stars and galaxies. Deep learning, for example, stellar spectral classification, galaxy morphology. So a different technique to address a different problem. And that becomes a very important example. How do I apply, which technique do I apply? Okay, so let me quickly come to one particular problem. I'll run through it fast. Okay, the general problem is galaxy morphology. And galaxies, as you know, contain about 10 to the 11, 10 to the 12 stars. And they can be spiral galaxies like ours, they can be elliptical. There are all kinds of features. For example, some of these galaxies are bars, some of them have rings, Some of them have been pulled out, and there are two galaxies here which are interacting, all sorts of things are there. And we want to learn to recognize that. And you see, the thing is that the happy situation where you can actually, with a telescope, look at galaxy morphology, doesn't last when you get to large distances. You see, each one of these is actually a galaxy. It's just a blob. But is there information? And so now I'll quickly consider one single problem, is that how to distinguish between stars and galaxies and quasars. You know what's a star? The sun is a star. If I take it to a large distance, look at the point. The Andromeda galaxy, which all of you would have seen at least in a picture, has beautiful spiral. But if I take it further and further and further, then it becomes smaller and smaller and smaller. Okay, at some point, you can't distinguish from the star. Right? But there is some information. Because a star is so small that when it's in the sky, it's actually a point source for all practical purposes. But because of the broadening of the atmosphere, if you're seeing a point, you see a disk in the star. And it has got a Gaussian distribution. Whereas a galaxy, even though if it becomes at sufficiently large distances, it cannot be, it will just sit on one pixel. And then you really can't distinguish it from the star. But otherwise, if it is closer by, there will be some small differences between them. Okay, so you see that this is a star in the field which is at high galactic latitude, away from the plane of the galaxy. And every dot that you see here, okay, so is a galaxy. There are very, very few stars. So this kind of small dot would be like 10 to the 11, 10 to the 12 stars. And so the way to get money to do this kind of work is to tell people, companies, what big marketing opportunities there are. Okay, so because just imagine the number of civilizations in just one dot here. Right? So you see that here is what is called a Gaussian shape of a star. Then this will be here actually. So this is a bright galaxy, and its shape is quite subtly different from that. And a faint galaxy, because the signal to noise is very poor in cities. So long ago, this was in 2002, Sajid Philip, who was a very long coordinator, and Yogesh Vardekar is sitting there, so he was a student, and Babu Joseph was his guide. So we are talking of decades. So you see that what we did was that we looked at a small number of galaxies and stars from that particular field I showed you. And Yogesh and Sajid actually looked at this, said that these are stars, these are galaxies, these are stars, these are galaxies. And we measured 3 parameters for that, okay, which had to do with how big it is, how the light falls, etc. 3 parameters. And those 3 parameters were input to a specific kind of ANN called the difference boosting neural network, which Sajid had derived. Right? And then and you see that we have got the data. If you look at the data, hundreds, so many galaxies, so many stars. If you try to send this kind of a paper for publication, they will just laugh you out of it. But at that time, it was state of the art. Okay, so you see that now, and then we got 97%, 98% accuracy to be able to distinguish between. So again, this probably was because of what's called overtraining. So then, now a similar problem, distinguish between a star and a galaxy. I'm sorry, a star and a quasar. So what's a quasar? A quasar, you see that this one will be like emitting like the sun, which is a star. Maybe 10 to the 33 volts per second. This one emits 10 to the 45 volts per second. It 10 to the 12 times more than that. So where does it come from? It comes, I mean, if you go by the standard story, it's at the center of the galaxy. There's a supermassive black hole there, which is accreting mass, and then it becomes super. Now, because it is such a compact object, exactly like a star. So how do I distinguish it? Then it turns out that this is a spectrum of different kinds of stars. They're typically a black body kind of spectrum with absorption lines. And this is the spectrum of a quasar. It's completely different. So what it means is that if I look at it, the colors will be different. But colors, the blue color, red color, white. So you see that here the plot, the different kinds of objects, quasars, white dwarfs, and stars. And these are the stars, and here are the quasars and white dwarfs. And so you see that by using these 2 colors, this is ultraviolet and blue color, this is blue and visual color. By using these 2 colors which can be measured, I can separate them. but the separation is poor. So then what do? I say that look, let me look at different colors. Right? So then each color space, there is some separation there. So if you look at a multi-dimensional view of it, you see that when I look at the color space, abstract color space, look at it from different directions, I'll get different things. So use it all. What happens is that there are only measurements of 5 different filters. It gives you 4 colors and then say how bright this is and what type of object it is. So the input data are the colors. The output is that this is a quasar, this is the star. And so we used ANN to do it, and look at this nice accuracy. And here we used tens of thousands of objects, and then you can see here it is contamination 1.41%. Okay, meaning that 1.41% wrong, and these are the misclassified objects, and these are the classified objects. So we first started with just a few hundred objects and used ANN. And here also it is an ANN. Okay, but then we could use far more objects because the technology was better, and we had learned more by them. And this work was done by Shiru Abraham when she was doing a PhD, and this must have been about 15 years or a little bit more. Right, so after catalog. Now look at the modern era. When in this particular, I want to distinguish between stars, galaxies, and quasars using deep learning. And so you see that these are bright galaxies, these are the medium bright galaxies, and dim galaxies. You can hardly see them. And this is a star, and here the quasar that I showed you. So try to distinguish between them using deep learning. And then what happens here? So the very important thing is that these 4 students, they approached me during COVID. 2 of them were from IISER Bhopal, one from IIT Bombay, and one from, I think, VIT here in Pune. And they were friends, and they said they want to work on something, and we started working on it. And it has been an extremely productive relationship, meaning that one of them went and did a project with Ashish in Pasadena, and then lots of 3, 4, 5 papers have come out, and they continue to come out even though these people are doing other things now. So a very fruitful relationship is possible. Requires hard work. Yeah, finished. Okay, so you see that here, now when you want to do this, star identification, what we did was that we used AlexNet architecture and then deep learning. So just give it these images, it looks at it says, how do we know that it's a star or galaxy? In the past, we had relied upon Yogesh and Sajid sitting down and looking at those things. Now here we have got tens of thousands of objects. Okay, there's no way in which you can do it like that. But as it happens, there is this catalog called the Sloan Digital Sky Survey catalog, and that provides you information on hundreds of millions of objects. Okay, and then there is a pipeline. I'll finish it 2 minutes. So the pipeline processing, which tells you that this is which kind of an object it is. Okay, for a fairly large number of objects. So those are used in the training. Okay, and so those are used in the training. And then you'll see here that this is a CNN, Convolutional Neural Network Classifier. But then these students also did something interesting. As it happens, the Sloan also gives you parameters related to the object. So they could also do an ANN. And so this is not necessary, but they did it, so they combined the two, and the output was concatenated and put into a single network, and then they got very nice results. So you can see there are what about feature maps, okay, meaning that when you pass them through filters, what is the system looking for, and then you see that the different kind of experiments were done, and the answers are given in terms of this confusion matrix. Okay, meaning that either 98.5, 98.03%. So this tells you what percentage of objects are correctly classified and what percentage of objects were missed. So I would have gone into other examples. We can do that later, but I'll stop now. But I want to answer Durgesh's question. Okay, it says that how do I know when to stop? That was basically a question. How do I know? See, there are 2 things here. One is that you are minimizing a function. And so So the thing is that you just, if you are doing simple fit, you just minimize the functions in the answer. But you have to see whether the answer is good enough. Okay, because you fit a, like if you fit one function and you fit something else to it, and just minimize the error, and you make it a completely different curve. So you can't say minimum forget to nothing. So what you need to define, so then you'll see how much you just scatter. What happens here is that the situation is far more complex, and because you've got many epochs of training, and you do the training and you do the, then there's something called validation. And when you do the training, you will see that the function keeps reducing, the error function reducing, and then it can go like this. Okay, so do I stop here, do I stop here, and do I stop here? For that, what you do is that you do validation. Meaning that you have got a part of the sample which has been kept aside, and then you see how many of those you can validate correctly. Okay, how do you classify correctly? And that, whereas this curve goes this way, that curve can keep going down 1% correct, and then you can start going up again. And so what you do is that you stop at the point at which it is. There's no point in, because if you, there's no point in going further. And then the question is, why is it going down? Why is it going down? So that is because of a wonderful thing called overfitting. So what do you mean by overfitting? Just imagine I give you arbitrary points in a plane, I ask you to fit a curve, the best curve for it. You can actually take a curve which passes through every point. If I have a sufficiently high order point polynomial, you can pass it through every point. But if you give me a new point, it will not lie along the curve. So what happens? There is another thing called image augmentation. Okay, meaning that I never get enough galaxies for a training. So what I can do is that I can make the galaxy brighter and fainter. I can turn it, I can flip it, and use them. So the favorite question is, why can't you just take one galaxy and do all this? Why need 10,000 galaxies for training? If you do with one galaxy, you will find that the function gets minimized. But when you try to predict other galaxies using that, you will get a very bad answer because there is not information. Okay, so there are several curves that you need to watch. And then you have to say that now it's all right and now I'm happy. But then finally, the real happiness will come out of correct applications. Okay, if you have an accident, no matter how happy you are, you will pass. Okay, thank you very much.
What question for Ajit? What are the prior knowledge of number of classifications?
Oh, you mean to say the number of classes?
Yeah, so can we, is it a normal practice that if we are not identifying something as a class,
Yes.
then it is separated out as an unclassified object, which can be the quantity?
Yeah, you see, that is a very important question, an important consideration. See, for example, we did a program and we carried out an application where you have to classify stars. So look at the spectrum, and then there are a certain number of classes, and we divided the stars into those classes. And then you can do that for 10,000 stars, 20,000 stars. After that, what are you going to do? What is very important is to also identify those objects which cannot get classified. Okay, and then they may not get classified simply because the data is not good. But it is also possible that these are very rare objects which are not so. And so, unclassified objects can be of particular interest, depending on the context. Either it shows that your network is not good enough, or it shows that you're finding new concepts.
Yeah. So in the context, Fermi has detected upon blazars that are unclassified. If use around 30.
Yes.
So because we don't have the optical structure, so
Yes.
how we will distinguish it or
Okay, what I would do is you take those unclassified objects, okay, and then run them through an unsupervised. Okay, so in the sense that you ask the network itself to provide you the classification. So the network, depending upon what kind of network, it should be 5 classes, 10 classes. Okay, because there are things called clustering algorithms. So in statistics, so like that, there are also these applications of these neural networks there. and then you try to look for systematic synchronicity in the unclassified objects, and then you develop a better understanding.
I have.
Sorry.
I didn't understand you like non-linear model. How does value help such?
So, okay, what happens is that the non-linear model, meaning that you see, it is not ax plus by plus c is equal to 0. It can be ax squared, it can be things like that, it can be xy terms can be there. So what is, just look at the sigmoid, that is easier to understand. If you look at the sigmoid function, that the argument of the sigmoid function is something which is made up of all these things. Okay, for example, it could you just adding, we're taking the weights and making the function and putting it. But e raised to x is by definition a non-linear function. So it is that non-linear.
How is it happening in case of the value?
Yeah, because it is this way. I mean, for that you will need the hands-on examples. So you are going to do that on the third day. Yeah. Okay, then you'll understand it. It's not very easy. I also was completely confused by how does this not do that.
Yeah, maybe.
So can this machine learning algorithm be used for other applications and classification? Inference model or general?
No, I'm sorry, I couldn't hear you properly.
So this machine learning algorithm, here you showed example for where you want to classify some object.
Yes.
So is there any other application other than classification for any inference problem that can?
Yeah, you see that those theorems which I talked about, so you can define any function. So which means that the kind of thing that you do, okay, they fall into either regression. Okay, when you say regression, it means that if I give you x, then I need to know the value of fx. And so when fx is there are two values, 1 and -1, it becomes a classification. But if I give you x and then I want to evaluate x as 1.964, then it becomes a regression. And so most problems that you want to see can be divided into these two separate things.
Thank you. What we do for discussion during the breaks and over the next 2 days. So it's not like more questions.
Yeah, I'm not available today, but tomorrow I'll be around. We could. I mean, I'll be perfectly happy to at your off time when you finish just to show you some more examples.
So the next set of talks are going to be given by Siddhant Mishra. He's from JPL. And these talks are about some of the recent advances like foundation models, large language models, generative models, and so on. We'll start with a little bit of deep learning as well. And at the end, he's going to provide with several libraries that you can be using. Because what has been happening of late is that the code development has been so good in the industry overall, is that you don't have to be code cowboys and write much of the code yourself. It's much more efficient to take libraries that exist outside, be able to string them in meaningful ways for your problems. And for that, having access to or knowledge about many libraries is the crucial. So that's something that we'll be getting into. And during the talks, if you have very pertinent questions, you should feel free to interrupt if possible. The questions will be answered there and then, but otherwise the flow can continue. But let's try to make this more interactive in general. And there are also a few seats here, by the way, for people sitting on the sides. There are empty seats, so please come and sit there. Okay, so Asiran, over to you.
Am I audible? Hello.
This? Oh. Am I audible? Okay, thank you, Ashish. I think my talk is a good segue from what Mr. Ajit has presented. So I'm going to be presenting a little bit of similar things in the beginning, but not into as much details. So this is the, let's see how this works. Okay. So I'm a senior data scientist at NASA Jet Propulsion Lab, and I work on a lot of applications for intelligent system, machine learning, AI. I have a little bit of specialization in natural language processing, but I pretty much do any type of machine learning and deep learning or classical machine learning if there's a need. So let's begin. So the first segment is deep learning. I'll be covering a bit of stuff that Ajit sir has covered. So deep learning is a specialization of machine learning, which where we use artificial neural nets. They're inspired by the brain neurons and how they work. So as Ajit sir has also described, there are some inputs like too far, like x1 and x2. You create a weighted sum of those inputs, then you apply an activation function. The activation function, what it does is that it introduces non-linearity into your model. It could be understood as if you're learning a language, then you need enough number of words so that you can describe an abstract situation, you can do poetry. So the more of these types of interesting things you want to do, the more capacity your language needs to have. So similarly, non-linearity is introduced so that your model can create curves as much as possible so that there is a capacity. It doesn't mean that it has to do it. But if you don't introduce that capacity, then it can only create straight lines for separations. But we want there to be curves for the separation. So that's kind of one reason why a student asked why you introduce non-linearity into your models. Now those are called a node. So you can see in general in deep learning, deep is a misnomer. So usually if it's 2 or more number of hidden layers, then you can say it's a deep neural net. So there's some input nodes, some hidden nodes. Hidden nodes are not actually hidden. It used to confuse me at some point. Then there's the output layer. Now each layer in any layer, each node in any layer is connected to every node in the other layers, and in the layer next to it, a previous and the next layer. That's the fully connected neural network. It's the most basic fundamental type of neural network that people usually begin with. It works fairly well for most of the problems. Now here's a very simple architecture. Generally what happens, there's a feed forward. So you take your input, you convert it into input vectors. So some floating point, integer numbers, something that could be inputted as inputs. It goes through the forward calculation of weighted sum. Activations are applied to each node, and so it moves forward. And in the end, you get an output. Usually it's a supervised learning problem, so you need to have the right answer. So when you get an answer, you compare it to the right answer, and you use a loss function to create an error or a loss. The whole idea is to reduce that loss, but you reduce that loss not for one example, you reduce that loss for a batch of examples. So sometimes it's also called a batch learning. Now, what really happens? How do you reduce this loss function? So what happens is that each connection here has a weight. Now those weights we start with an arbitrary set of weights. Now, once we do the forward pass, in the backward pass, each weight is adjusted a tiny bit based on, so that when you do another forward pass, the loss has reduced a little bit from before. It can happen really fast or it can happen really slowly. It depends on your learning rate. It's very important. If it will happen too fast, then there's a chance that it will not find the minima. but it should have not a slow pace or a very fast pace, but it should be somewhere in the middle. And so learning rates are pretty important. So every forward pass, we calculate things, and in the backward pass, we adjust the weights so that next time we get closer to the right answer. Let's move forward. It could be thought as finding the minima. So if there's a lost surface, you can see that with every backward pass, it's trying to find the minima. So each step is a learning rate. So you can imagine if the steps are too large, you might pass the minima and go to some level. Please.
Local minimas or global?
So I will not go into the theorems of it, but the way it is learned, it tries to find, so theoretically, it will find a local minima. But if the learning rate is good enough, it has been shown that those local minimas are usually pretty close to a global minima. Yeah. But again, it will go into the mathematical theory of, so kind of in between, not really the most basic local minima, not really the most optimized.
But the ultimate aim is to find the global.
Exactly. The ultimate aim is to find it. And that's where the art of doing deep learning comes in. How do you go there? Please.
So is it parallelly also working on finding the minima? So while we are finding a solution, whatever we want, at the same time, there is something parallelly going on which finds and keeps track of the minimas.
It's actually the other way around. It tries to find the minima, and during this process, the solution is already found. Because the minima of which it is trying to find the minima of the loss function. And once the loss is reduced, the loss is basically the difference between what the network can predict versus what the right answer is. So when you reduce that, it already becomes closer to the solution. So it's the same process. Yeah, just a different way of understanding it in different way. So we'll jump quite far now because I think Sir has covered a lot of things, but I'll give you some flavor of everything. So I think the idea is that by tomorrow, when we have some use case lectures, you guys all will be machine learning, deep learning experts. But jokes aside, you guys will at least know that, oh, I've heard of this before. I know a little bit of how this works. So that's kind of the general idea. I will not go into a lot of mathematics of it. Let's talk about autoencoders. It's a very interesting unsupervised learning approach. It has this, so let's focus on this diagram. It has input, encoder. There's something in the middle. It's called a latent representation or a vector. Then there's the decoder and the output. Usually the encoder and decoder are mirror opposites of each other. So So if you see here, this could be, so this is the convolutional neural network that Sir has been showing. If you take an image, you can gradually reduce its size, but you can increase the number of channels that may represent different features. So you're basically compressing the representation of an image. And in the end, you get like this tiny vector that has a lot of knowledge about images and underlying principles of how images are look like, how a nose looks, if it's a human face, what are the lines and things like that. So this is the same thing. It's a smaller representation of the larger input, and the encoder makes it possible. This could be an encoder. It could be a fully connected neural network. It could be really anything that converts an input into a vector. Really anything. You can put there anything. It has to be a neural network though. Now, if you reverse the process, that's your decoder, and it will create the output. Usually the input and output have same modalities. So if the input is an image, the output will be an image. If the input is text, output will be text. Okay. In this process, so it's a very interesting thing here because you don't need labeled data. So if you have a lot of images, you can pass it through, then the output will create some garbage image, but you have the actual image that you fed it through. Now you'll say, this was the image I fed, you're giving me garbage. Can you bring it closer to the real image? And that's how it learns. And then it will update all the weights, it will start learning. So what it's doing, it's just reproducing the input in the output. And after you have done this training, which is unsupervised because you didn't label the data, you just collected the data, you get this nice representation of that data set. And so this vector becomes very important. Now you can split the encoder and decoder, and you can use it for different applications. You can use the encoder to encode a lot of your images. Now you can use that smaller representation in learning other neural networks, or you can use, so if I input my face and Ashish's face and get a representation and have a similarity, we can create a similarity. It'll tell me how similar my and Ashish's face is, or how similar my or my dad's face is. So things like that are possible because now you have this hidden representation. You can do a cosine similarity between that. So it's very important. Decoders, I'll talk a little bit more about what the use cases are. It's also very useful, but let's move ahead. There's another interesting encoder here. It's for sequential data. Sequential data is like time series data or text. One word comes after another. So here x1, x2, x3 could be different words. So this is very interesting because one word is considered at a time. So it goes through an LSTM. This is also a network. I'm not going to go into the details of it. It's called long short-term memory. So just assume this is a neural network. It creates a hidden representation. When the next word is inputted into the same network, we also input the representation of the previous word. So you can see that here to get the representation of to input the third word, I have to wait for the first and the second word. With sequential, you cannot parallelize it when you're implementing it, so it's slow. The other thing is that when you're at the 100th word, it might have already forgotten the first word. So that's why, LSTMs are a type of recurrent neural network. LSTM tried to improve that capacity of to maintain that dependency between long distance relationships in sequences. So it tried to make it a little bit better. There's even more advancements in that. But it's the same thing, as I said, you can do anything with encoder. You can put anything in encoder and decoder. So here I've put an LSTM here. The decoder is the same, the LSTM. So here you can use it for translation. English can go here, Hindi can come out from the other side. Moving ahead, transformers. So you might have heard of transformer. They're super popular right now. All of the foundation models are using the transformer architecture. This is actually the improvement over LSTMs. Here you can see these three words. They have their own hidden representations, and they don't need to wait for the previous or the next word to be encoded to get their own representation. So they could be parallelized. Each word, the hidden representation could be calculated in parallel. Now, that was, so there are a few contributions of the transformer model. There's a paper which came out called Attention is All You Need that changed everything apparently. And some of the concepts of what a transformer model is from how it's different from previous models. So I talked about LSTM, how they cannot be parallelized. They work on sequence data. This is the same, it can work on sequence data, although it could be parallelized because there's something called self-attention. So the mathematics of it is, so self-attention means that each word knows how it is related to every other word. So here you can say once it is trained, you can provide this type of connection where if there's a sentence, in this sentence, you can create a nice graph saying it means the animal or how it's related to the other words. So same you can do with every other word. That's because of the self-attention mechanism. Another thing here is that in LSTM, you can see that since everything is happening sequentially, every word knows where its relative position is compared to other words. Here, each word it knows how it's related to the other word, but it doesn't know how it's positioned according to the other words. To do that, we have to artificially input an embedding, which is called it leads me. A positional encoding, yeah. So you have to. So that was another contribution of this paper that made it possible. Now attention, which started off with text sequences, it's being used for video, images, everything. It has been adapted to those specific.
Yeah, so what does relate mean? So if you have two words, if you say it is related to the animal, or the mathematical, what is the mathematical form of the idea of relation?
So here the relation, the idea is more of a semantic relation. So when you're writing a long sentence, you use pronouns. So it's, I think, the most easiest example to give. So it in this case is not referring to the street as much. It's not referring to I think anything else, but the animal.
Absolutely, yeah. But I'm just trying to understand how do you do this mathematically?
Talk to me later. We will talk about how to do it more mathematically. But
So I was asking about the rankings of the positions of these items in respective domain.
So the rankings, yeah. So the rank it gives you get a score for each word compared to each word. So how relevant all these words are compared to one single word, and so you can do it for all. So you get a score.
So that is the rank.
That is the rank. Yeah. Those are the attention values. But the concept of attention was present from before. They introduced something called self-attention. In attention, it was more of like when you have an output and you have an input, say you have a cat or dog image, and then it's predicting, is it a cat or a dog? What attention used to do was you can you can visualize where exactly the cat is, kind of like the activation areas of the image. In this self-attention, it's called self-attention because the input itself is attending to itself. The output is not attending to the input. The input itself is kind of self-aware of how I'm related to other inputs.
Is this self-attention a neural network that is being trained as you go on, or is it treated?
It's being trained. Yeah, it's a good question. Yeah, I'm going to switch over to generative models, but if you have any other questions. Also, I think the time is running out, so I'll move forward and then we can talk later if you have more detailed questions. So generative models, they're called generative because they can generate new data, which is very realistic. It's not real, but it's learned from real data. So it can see all our faces and it can generate a new face that looks like a human, but that human doesn't exist. It got really a lot of popularity on the internet a while ago. So that's why it's called a generative model, because it understands the underlying principle of generating a type of data, and then it generates that data, which is very realistic.
Similar to simulation.
Yeah. So so generative as opposed to discriminative models. So discriminative models were more popular before. What they would do is they would take an input and they would discriminate the input into predefined categories. That was kind of the general ML before. After generative models, it has been changing. I will cover two generative models. One is variational autoencoders. You guys are expert on encoder-decoder models or autoencoders already. So I'll talk about the variational aspect of it. Now, it's the same as before. There's an encoder, there's a decoder. But what they found was that instead of outputting a vector, which is a sequence of numbers representing any input, they started outputting a distribution. So to output a distribution, you have to output the parameters of the distribution. So here they're outputting the parameter of a Gaussian distribution. Now, as a second step, they sample from that distribution. So they don't take the exact vector that has been created by the encoder, but they sample from that distribution, and then they decode it, and that creates the output. And that changes everything. You know, that's the only difference. I mean, there are other things too, but that's kind of the main difference between autoencoders and variational autoencoders. So what we learned before and what generative models can do. So you can see this could be a latent space plotting of one of the vectors, and now it's this. So you see this area around it. It's the distribution of it. So you can sample anything from this area. This is a good example of if you just train an autoencoder for MNIST data set, which is a handwritten numbers, and you visualize that latent space that you can, and then you color those clusters based on the labels of it. Is it 1, 2, 3? You can see nice clusters, right? Now, if you take a sample from this here, which kind of is in the middle area, and you try to generate an image, it'll be garbage. That's basically what was seen in autoencoders. So that's why they changed it to variational autoencoders, and that's why they created a nice flowy distribution. That gives you a little bit more continuous space, right? So that's why now you can create more realistic examples, or examples which you've not really seen in your input data. You're not recreating your input data, but you're kind of doing slightly different than that. Okay. GANs, or generative adversarial networks, again, very popular. In practice, they work better than variational autoencoders. So you'll see more of these being used these days. The concept is very simple. You input, so here the generator is a decoder. There's no encoder here. So you take a random input vector, like random number. It goes through a generator, which is a decoder, basically, which takes a vector and generates an image, let's say. So you generated an image, let's say it's a garbage. Then you have a real example. You give it to a discriminator model. This is another neural network, which what it tries to do is we have given it a task of see two images and try to tell us which one is real, which one is fake. There's a binary classifier. So this binary classification is nothing because we already know which image is real, which is fake. But the discriminator doesn't know which image is real, which is fake. We've hidden that information. So whenever it outputs a fake image as real, we give it a pat on the hand saying, do better. If it does the opposite, we say, no, do it better. So in this way, the discriminator learns to do the prediction really well. So it becomes really, really good at predicting what is real image versus what is fake image. And in the same process, the generator becomes really competitive. It becomes really good at generating very real-like fake images because its task is to fool the discriminator. And discriminator's task is to catch the generator. That's why it's called adversarial, like an enemy. And all of this is trained in kind of a single pass. So none of this is pre-trained. It's all trained as things go.
What's there in the discriminator one? What network is used for the discriminator?
So in discriminator, you can use just a feed-forward, fully connected neural net, or anything really. So if it's an image, you can use a convolutional neural net. So the discriminator could be an encoder type of network where it takes an image and it generates an output type of thing. So something like an encoder, and this is like something like a decoder. So I want you to be very clear on what's in encoding and decoding. Encoding takes some sort of real example of sequence, text, image, converts it into some sort of like a series of numbers, which you will not understand, but it could be very useful. It's a representation of that input data. A decoder does the opposite. It takes that number and it creates a more realistic, human, understandable modality.
So eventually, does one win or you depend on your task?
So there's I mean, yeah, you can say at any point if you stop, you can check if the discriminator, how well it has performed against the generator or how well generator has performed. But that's not really the point, you know. We want both to develop at once. So, please.
So here you're starting from a random input vector. How do you go from here to a generator model when you say that, okay, I want this kind of a feature to be there, or this, I want, you know, what you see with DALI or something that we have.
Very good question. So that brings us to the next slide. So far, it's not as useful. What you're doing is you're sampling just random noise. You're giving your model a random noise, and you're expecting it to generate something that looks real. I mean, it sounds really amazing, but what use do I have for it, right? Like, I mean, it could be a good game, but it's not useful as much. So there's something called conditional generation. It's pretty much what you already learned, but it uses an extra input into your system where you have, for example, a lot of images. You know that whose images are these. So you also try to put that information when you're training. So when you're training for human faces, so if you know whose faces, if they are celebrities, you know whose faces are these. So you also give an input that, oh, this is this celebrity, this is Amitabh Bachchan or something like that. And because it knows that information, it can learn to associate that extra input, which they call condition. So now that it has learned to associate any generated image with kind of a real world label, it can do it even for random noise. So if you generate a random noise, it knows that this looks like Amitabh Bachchan. Now, you know, it's not, but something like that. So here's an example actually. So what you can do with the conditional thing is that it can generate an image, but you can say, can I have blonde hair on that image? And it can do that. It can regenerate the same image, but with the hair color a little bit more lighter. Or with, so a lot of art applications have come up with this, fashion industry applications have come up. On the right, you can see that it can be used for style transfer. So if you have an image, and the network has learned using, suppose, some famous painters' images, so it knows how to produce a famous painter's image. If you give it random noise, then if you, in the conditional input, if you give a dog's photo, it will merge those two and generate the dog's photo in that painter's kind of style. So that's where it starts getting very useful. But the use has not stopped here. It's we will talk more and more on the next set of lectures. But when we talk about foundation models and other things, so should we take a break? Okay. Oh. Yeah. Please.
Okay. Backwards for better to have a better noise. Like if you have an image with noise and you know you have an image without that, so can it be used to modeling the noise better?
Yeah, it's a very good question. It's called diffusion. We'll talk about that in the next set of slides.
We're almost ready for tea break. I guess we can discuss during the tea break if there are more questions, since we are also running late. There's one request outside on the board. You will find a pen and you can just stick against the name so that you know who is attending it. Okay. Yes.
Comparable to what. So for that, I'm actually trying to increase my. Like, I begin.
Yes,
I
yes.
found out that how many.
You are using. This data set itself.
I'll have to ask. I don't think it's difficult. Because then it's done. All I need to do is take this data set and done. It's done.
But you are positive that your problems are caused by the
Yeah, because like,
small size data set.
because in the sense that my data set is 1/5 of what he. Yeah. And it's like yes, 5,000.
I guess it's not. I can.
What do you want?
So as you said,
We like it.
but
Yeah, we have
the
to see
beginning,
it. It needs to be announced.
we need to announce the instructions about what they should expect and plan for the last day.
I tried to transfer my data set and it's like 2.2 GB. So I transfer it.
So साक्षरता की आपण how do we get link to IUCAA? We invited to the IUCAA thing, right? IUCAA site server.
No, there is no IUCAA size.
Okay.
This is just size server. And then we will make our data sets public. And then people can just
Access it.
Okay.
Okay. I made an account. I will.
Size server. Yeah. People are also. काय स्लाइड्सला नाही माहिती काय करतेस तू बापरे मल्टीटास्किंग
I need to know something.
This is my cricket.
It's also a present project.
आंसर बोलने वाले
Yeah. All right, is everybody settled in? Okay, so we're going to continue with Asitam's talk on foundational models, and we're going to go much deeper into machine learning and large language models. But before we do that, I had a couple of logistical instructions. So for the hackathon on day 3, as Ashish mentioned, it's not a traditional hackathon. It's more of a brainstorming session where you can produce ideas and then go forward. But we need to do a little bit of planning for that. So there on the poster boards outside, you can see there are blank sheets of paper, and we want you to write down your ideas. What would you like to do? Okay, and if there are data sets that you think would be interesting, and you can write down, describe in brief what the project is, what data sets you have, what data sets you're looking for. And if you're interested in some of the existing projects which are already on the board, you can sign up for it. You can put down your name, perhaps your email address. So at the end of tomorrow, before day 3, we'll go through those projects and select out the ones which are signed up heavily or have a lot of possibilities, and we can discuss those further. Not to say that the others won't be discussed at all, but we can choose the ones to focus on. All right, so please do go ahead and write down your ideas or sign up for new projects on the sheets outside. So with that, Asitam, we can start ahead with the session. Thanks, everyone.
Hello. Am I audible?
Yes.
Yeah.
All right. Cool. Okay. Welcome back. So, continuing in the same progression, we'll talk about foundation models now. Some of you must have heard of it. I'm sure all of you have heard of it. Just maybe some of you don't know that they're called foundation models. So foundation models are really large models. As Ajit sir was saying, people are spending billions of dollars in training these models, and they have millions and billions of parameters. They're really, really large scale models. And the reason why they're called foundation models is because they're very fundamental models. These models, once trained, they can lead to a lot of learning and training and experimentation in the same domain on different tasks, and sometimes in other domains as well. So we'll see some of those examples. I'll try to keep it exciting and make sure that you guys, at the end of the day, get a good idea of what's available out there, so that when you start doing or using these things, or even brag about it to your friends that I know about such things. But so foundation models, they're really large scale, as I was saying. They have billions of parameters. They cost billions of dollars. Not all of them, but and they're trained on a very, very large amount of data. Again, in millions and billions, and sometimes in trillions. And where do we get all that data? That data is gotten from the internet. Now, with machine learning, people who know anything about machine learning, you know that, or deep learning, you need labeled data. You need to, if you have a lot of images of cats and dogs, you also need to have a string or a label that these are images of cats, these are images of dogs. That's an expensive process. It's a manual process, or has been in the past. So it's difficult to get a lot of tagged or labeled data. So where are we getting all this large data of like millions and trillions of images and text to train? They're not labeled really, right? If you find an image in the internet, the image itself doesn't tell you what it is, right? Maybe in the text somewhere it says that, but the image doesn't say that. So, but they are trained on these large data sets. We'll talk about how they're trained on these large data sets without no labels. We touched about it before too, so it won't be a complete surprise. Pre-training. So pre-training is the process that uses this unlabeled data to do some sort of unsupervised self-learning approach. And during this process of pre-training, the model learns a lot of underlying patterns and principles of the data sets. For example, with large language models, ChatGPT, with the pre-training, they will learn how English language or the other languages really work, how they relate to how sentences are created. So kind of underlying theories of it. They learn it automatically. Then comes the fine-tuning. Fine-tuning is the process where we use the pre-trained model and we ask it to do certain machine learning tasks. Like we'll ask the pre-trained model to do text summarization, question answering, or classification of certain things. Now, these are called downstream tasks, and that's where we are teaching this foundation model how to solve problems, not just know about the patterns, but how to also be able to solve problems. So, and this fine-tuning is done in a supervised way. You need a labeled data set for this. So it's a smaller scale process. Transfer learning. Now, once your model is trained, you can do something called transfer learning because your model is a foundation model, it's a fundamental model. You can now use the same model to do new tasks that it has not been trained upon. So suppose it was fine-tuned for summarization, but then in transfer learning, you can also use the model or again, train it for a different task, like question answering or any named entity recognition. I'll give an example of named entity recognition later on. They're very versatile. They can be, once trained, they can be, as I said, used for multiple tasks. And they have some emergent behavior, which means that they have been not trained for those things, but out of the box, without any more training, they can do those things. ChatGPT, for example, can solve very simple math problems, or if you give it a pattern, it can repeat those patterns. Some basic stuff, because and it has not really learned to do mathematics. It has just learned to how language works. And in the process, it has seen things, and now it can correlate those things, and it gives you like kind of an idea that oh, it's doing some mathematics. So they're very versatile. So some examples. One of the examples is called Segment Anything. It was open sourced by Facebook. That's an MRI scan and of the human body. It's an axial scan, and Sam can out of the box create masks for it. It can segment it. You don't need any inputs. It can tell you that these areas look like there's something over there. It will not tell you what that thing is. It will not tell you which is a pancreas, which is a stomach, anything like that, but it will segment those. This is a very hard problem if you're doing manually. So you can imagine if you're a big screen, you have to create those contours and lines. Now you can automate that process. This model can do different types of prompts. It can do point prompting. So if you give the points of where you want the segmentation to happen, you can create a bounding box in your input image and it will segment inside the bounding box. You can create a rough mask and it can perfect that mask. Or you can do some text prompting. You can say, segment this particular thing. So if it has seen it before, it knows how it looks and it can do it. and obviously the image. So very useful model these days. It used to be a very difficult problem. Now we'll talk about the language capabilities specifically later on. Another one is DALL-E. You guys probably, it's very, very popular. I'm sure all of you must have used it in some way to generate your new profile pictures on Facebook or do any sort of like picture of an astronaut and riding on horse and things like that. So it can generate these images. It will probably remind you of the conditional generative models, so that text is the condition in the generation process. But the input is just random noise. It's just based on the condition, it can generate this image. Although DALL-E was trained on a very different process, a very different unsupervised method. Someone said here, someone was asking a question about it. It's called diffusion. So what happens? Again, it's an unsupervised learning process. We don't have labeled data, we just have a lot of images. What do? You take the image, you progressively add Gaussian noise to it. And so you create a series of those images. Now you ask your neural network to, you give it, I can use a pointer, I guess. So you can give this image and you can ask it to predict the next image. And you can give this image and predict this image. So slowly you can ask it to denoise. And in the process of just this simple task of denoising, it starts learning how a dog or a rabbit looks like, what are the contours of a human face, anything really. And models like DALL-E are trained on a huge amount of internet data. So not just cats, dogs, and rabbits, it can learn literally any, like most of the things that you can find on the internet if the images are available. It knows what they are, how they look, how to generate the image, how to generate a different type of image for the same thing. And it's all done by kind of the basic principle of diffusion. There was something called stable diffusion as well that came out later on. So now, compared to autovariational encoders and GANs, it was seen that learning from diffusion can create more photorealistic images. It will not create an alien for you. It will create a more human-like, a more what we can understand. So that's why the diffusion models became very popular a while ago. Now, we'll talk about in diffusion, you're only learning the image. There's nothing about language here. How do we introduce language here? So the introduction of language was a very interesting thing in DALL-E, which was done using a model called CLIP that came before. And this model is another foundation model that learns the relationship between images and text. Again, CLIP was trained on a huge amount of internet data, labeled data, And some of the label data that CLIP used was actually generated artificially and captioned artificially. So all these models kind of help each other in generating new data, learning from them, or using pre-trained models and things like that. Let's talk about how CLIP. So another technique that CLIP introduced or maybe perfected was contrastive learning or contrastive pre-training. Contrastive learning, I think, existed before. They used the contrastive pre-training for this purpose of embedding images and text in the same latent space, which has been done again, but not in this exact manner, which makes it super efficient. So you can see it takes a bunch of captions and a bunch of images. So we know which captions belong to which images, and it creates this matrix. So these are all the encodings. So you see the encoder comes again. Someone was asking why is encoder useful? So again, you see encoders will be used everywhere. They're super useful for creating these compressed representations of any input. So again, you create n inputs for image text, then images, and then you do this dot product and create this matrix where you can see in the diagonal is basically the right answer. All the others should be 0. The diagonal should be a score of 1. So the learning task for contrastive pre-training is to maximize the diagonal scores and minimize everything else. So that's the learning problem in this case. And using this learning problem, they have trained their model. And once you've done that, the interesting thing about CLIP was what they claimed was that all the like before, when you use a discriminative model for doing some sort of classification, you need to have so classifying dogs and cat images. You have to define the categories as to I'm going to classify only cat and dog images, and then you can create your network. What CLIP changed was that now you don't have to define the categories anymore. On the fly, if you have the CLIP model, you decide I'm going to be classifying farmlands from mango trees today, and it can do it for you. You don't have to create those categories and things like that. So because it's been trained on such a large number of training data, so
what decides the length of this data? Is it equal to the number of images that you have given?
So if you have a batch of 100 images, so each will have a vector representation. Now each vector has multiple dimensions. It's not shown here, but each one is like one image. So it could be 100, 200, depending on your batch size. That's a learning design decision.
Equivalent to the batch.
It's equivalent to the batch size, yeah. And then so once trained, you can do things like that. You can encode any new text and your image, and you can find the similarity. You can compare the vectors and see which vectors is most similar to that particular text, and that will basically become your right answer. So you've created an all-purpose classifier, text classifier. So this was kind of the learning task. So it can do things like this now. You give it an image and a bunch of descriptions. It can tell you which description most closely describes that image. This is very useful because now this model could be used by other foundation models to either generate data or just plug it into as their language unit. So Dolly used CLIP for their language training.
Just like in the variation autoencoding, is there a way to make this into a distribution entity?
Is there a way to make this into a distribution? So this is a very different learning problem. There is a latent space here, and all the generative models have a distributed latent space. In variational autoencoder, it is very explicit. In others, it's not as mathematically explicit, but fundamentally they're doing the same thing. So here, as long as it's a generative model, it will have a latent space which is continuous. or semi-continuous. So you don't have to explicitly do it, but with variational autoencoder is very explicit. You can visualize and do things. So it's very nice. Others it's not as direct.
But each of these vector images, let's say we take the vector corresponding to images, this can be converted into a distribution. We can manage the distribution.
Yeah. So here, so you see here is an encoder, right? So I think in this case, you're just encoding, you're not decoding. So you're not doing anything with that distribution to make it into an image. So I think there's no generation happening in this case. So there might not be. Scratch whatever I said. Okay, so we'll move to large language models.
So in the previous case, one possibility is that by creating a generation, you can see what are nearby spaces. So if you are inputting a dog, what is near to that dog?
Yeah.
So you want to do something like that.
Yeah, so as Ashish said, it does generate a latent space. Vectors are there. So and it is clustering those in that latent space, different things, which are related, which are unrelated. So there's definitely that representation going on that you can use to find similarities. Large language models. So this is a type of a foundation model. Again, mostly for language. What are the common use cases of large language? I think everyone has, if you've not, then please do, used ChatGPT to do one thing or another. They're very interesting things, and as I said, they have a lot of emergent behavior that they were not directly trained upon, but they could be used for those things. You can create a new problem statement, and you can actually make them solve that problem if it's in the text domain. So it's very interesting. You can do text generation, you can do translation, you can do question answering, you can do text classification, named entity recognition, code generation, and content recommendation. So some of the more popular things, but really the list goes on and on and on. It depends on how you want to use it. People are still finding new use cases and applying it to their field of work. So really sky's the limit here. I took some content from the website of IUCAA, and I fed through ChatGPT and I asked it to do NER detection, which is named entity recognition. It used to have its own models before. Even like 5 years back, you have NER detection models. They used to perform more or less okay. Now it performs really well. So you can see how it has separated out organization name, location name, person name, contact details, and things like that. And so, and again, it was not trained on this, but it can do it. So how are they really trained? What is the most basic way in which they are trained? Again, as I've been speaking, you guys must have guessed it that it probably has to be something unsupervised, because that's the only way you can train with a large amount of data when you don't have enough number of labels. And so there are two types of learning tasks. One is called mask language modeling. And so the basic training method for LLMs is language modeling, because they are language models, just large. In the mask version, you randomly mask some words from a sentence, and then the model tries to predict those words. In the causal language modeling, you just predict the next word. Okay, so not a lot of differences, but in practice, they have some more differences where one works better than the other for certain use cases. So there's a big field of research as to what works, what nuances work better than the other. So that's kind of the basic idea. Now, that stuff is just the generative, it's called generative pre-training. And we saw it before as well. Now, after that, there are some more steps which lead to GPT. Some of the main steps include then the supervised fine tuning. As I said, it has been trained on all the a lot of known labeled data sets that researchers have been using for NLP research, and it has performed quite well on those. But those are supervised fine tuning tasks. Then after that, so till that was GPT. For Chat GPT, it needs to have conversations, right? It's not just you told it to do something and it does it, but it doesn't have any memory from before and things like that. And I mean, ChatGPT is originally, they don't have a memory, but you feed the previous conversations. But still, I think the idea is that it should be trained on a conversation for it to become more efficient. So ChatGPT, and I'm not sure exactly if GPT was trained on reinforcement learning. I'll have to check, but this is another crucial step of reinforcement learning training, where and those of you who don't know reinforcement learning, don't think of it as something very complicated. When you're doing a chat thing, it's a multi-step process, right? So you start a chat. In the end, you might say, I'm this much satisfied with the whole conversation. Now that score needs to be given to every step, has to be distributed to every step of the chat. So reinforcement learning is a framework where a reward signal is given to all the intermediate steps. So it's the area of research where how to do it really well is researched in very, very layman terms. And so it was trained on reinforcement learning, and then what you see is GPT or ChatGPT. And this is a very simplistic view. It's way more complicated and involved process on how it actually done. Okay, so I'll skip this part, and if we have time, we'll come back to it. I wanted to show you how you can use ChatGPT on your own data, because ChatGPT has not seen your data, perhaps. It has seen internet data. But if you want to do something with your own data, how you can do that? It's a little bit more involved, but we can talk about it later. Please.
This ChatGPT, the LLM, also has relation to LSTM somehow, that they have to keep track of this conversation.
Yeah. So they both work on sequence of text. So that's, I think, the biggest relationship. LSTMs were used to a certain point, but then transformers took over because they were better at finding the dependencies between sequences. So if a dependency is like 100 words away, transformers are much better at capturing it. They're much efficient in training. So that's another reason why everyone switched to transformers. But you're right, it's LSTM could be used for the pre-training step. Yeah, but it might not be as efficient. Deep learning libraries. So this part is where you can learn how, or you can understand how you can implement or use everything we talked about so far without having to implement everything, even understand everything. But I do recommend try to understand certain things. So 3 libraries are very popular if you want to do any kind of deep learning. TensorFlow, which came first, got very popular. It was open source by Google, which they were using internally to train their models. I don't think it's very legible, but let me tell you, it's very complicated. The coding structure is very complicated. You have to define everything beforehand, and there's a lot of things that debugging is very difficult. To solve that came Keras. Keras was, there was a few people who were like, TensorFlow is so difficult. They're basically making a very simple problem very difficult because we're not all scientists or like data scientists or computer engineers. We cannot use such difficult libraries. So let's do something simple. So they created an API on top of Keras to make it very simple. So that same long code which actually I've cut short. Keras implemented in like very few lines, where you can see that it loads the data set into memory, into like test, train, validation. It defines a model, and they make it very easy to define models that are very popular already. Convolution neural nets and things like that, you can just like 4 lines of code. You can define each layer, or there are some predefined ones. You can define the number of nodes and things like that. So they make it very easy. Then they define a model on what kind of loss function there will be, what kind of learning steps, optimizations there will be. You just have to set those parameters. You don't have to do it yourself. And then you just call the fit method, where it will start the actual training. It will create a session and do the training. Then you can do the evaluation, which is again 1 line of code in this case. So super easy. Now there's something called PyTorch. Implementation and coding wise, I would say it's somewhere between Keras and TensorFlow. You have to still define more things, but again, it's not as complicated as TensorFlow. But the most important distinction I want to show here is that what happens in model training is things happen in epoch. So epoch, what happens is, so if you have 1 million, let's say 100,000 data points, in each forward pass, or we do the learning with batching. So you can have 1,000 data point or 1,000 image batch. So each batch goes, and then with the forward pass, the weight adjustments are calculated for the whole batch, and the model is updated in the one background in one update of the network. And so everything happens with a batch. So one epoch is when you've once learned through all the gone through all the batches. That's one epoch. So you've used all the data to train once. So similarly, you have to do it multiple times. You have to keep training on the same data, and then slowly the model starts converging. That is, the output starts becoming more similar to the real, the expected values. Now, here it's all hidden. You don't know that when from one epoch the next is going, you'll get output messages, but you don't control that. So if you want to do something between the epochs, you can't do that. And here, I mean, you can do it, but it's very difficult. Here is just a for loop where you can see that what are the images in each epoch, what are the labels, and you do the optimization and the backpropagation. And so it's very explicit. So you can change things much more easily. You can debug, you can see where it stopped, and you can output the values where it failed and things like that. So for doing any type of experimentation on new data sets, new problems, PyTorch is highly recommended. Once you've settled on an architecture, on a model, then use Keras or TensorFlow. Now, also whenever you use TensorFlow, you have to use Keras now, because Keras is the official API for TensorFlow now. So why not? So so once you've settled on an architecture, I would say use the Keras, because then the code will be very optimized. They do a lot of optimizations, which will make your learning really fast. Why does that happen? Let's talk about it. So the only thing is that PyTorch is slow. Keras could be a little bit faster, but more clunky when it comes to debugging. On here, you see, this is kind of a graph that gets created whenever you create a neural network. You can visualize it in TensorFlow and Keras. In Keras, it's a static graph. So you have to predefine inputs, hidden layers, outputs, processing, everything. It has to be predefined. Once you've defined it, then it starts a session, and then it trains your data, does the backpropagation, everything happens The difference, and here on the left, you see it's in PyTorch. As the code gets executed, very Pythonic style, one by one, the graph is created on the fly as the code is executed. So they don't create a graph before. So what it allows you to do is that in the middle, you can analyze your embedding or your data or your intermediate result. And you can, based on that, you can do the next step. Or you can change the network on the fly. So the definition of your network is not defined anymore. It could be dynamic. It could change with each input. So that kind of crazy things you can only do with PyTorch. But more recently, Keras and TensorFlow got, they thought, okay, PyTorch allows all these things, why not we can do that? So they have now an eager execution mode as well. So now everything you can do here, you can do there as well. So at this point, it's a matter of choice. It's a matter of like what kind of coding practice is good for you. But again, rule of thumb, when you're doing experiments, use PyTorch. When you're pushing your model into production, use Keras because they do optimizations. Because their models their graph is static. They know what calculations they can do differently or reduce. That here you cannot do it in PyTorch because everything is happening on the fly. So no optimization here. Again, now some of you might be thinking it's
Dynamic graphs, even though you change it between accounts, your code doesn't change.
With dynamic graph, your code doesn't change.
Dynamic graph, you said that.
Yeah, my code doesn't change, but my code changes the graph as the code is getting executed. It's a slight difference. So the compiler doesn't know, or the graph executor doesn't know what's going to come next. Like as the code comes, it will add a node there. And then when it does back propagation, it has the information on how it does the forward propagation. Accordingly, it will do the back propagation. It doesn't know beforehand. But in PyTorch, sorry, I'm getting into in Keras, it's predefined. So the compiler knows everything, what it's going to do next. It's not going to change on the fly. So it can do optimizations. That's the only difference. Okay. Now you might be thinking it's still very difficult. You make it sound like it's very easy. Yeah, please.
So does that mean you can choose to skip out on layers in Python?
Yeah, you can do anything. Like you can introduce a layer in one epoch, take it out in another, or I mean, not in one epoch. You can, based on your input, you can introduce or remove a layer. You can have 5 different types of networks, and based on your input, you can push the signal to any of them.
But in production, all the layers would be together.
All the layers would be together. It will be more well defined. So you can define, even in PyTorch, you can still define those things. So, but while you're doing experimentations, you might want to change it and do things. So debugging wise, it's very similar. So again, you can do those things even in PyTorch, but it's more difficult to do. Plus, those changes, if you want to print out something, again, very difficult. So they're almost similar. It's just the coding style is different. The coding methodology, philosophy is different from it. So we talked about TensorFlow, Keras, and PyTorch. But when you're doing a foundation model training, pre-training, fine-tuning, or any downstream task learning, there's a lot of steps are involved. You have to find the data. You have to do a lot of types of pre-processing like tokenization, masking, this and that, a lot of things. In a paper, if you read, they define all these smaller steps that they have done. Sometimes even in the glossary appendix. So they're very involved process, minute processes, that if you want to implement it, there's a chance that you will probably not implement it correctly, unless you found the actual code that they have used. which also they usually give the code for the model itself, not the pre-training. Oh, sorry, not the pre-processing. So then you have the model, you have to find the implementation of that exact model. You have to, sometimes maybe if you want a pre-trained implementation so that you want to do fine-tuning, you have to find that the model weights. Then you do maybe a downstream task. So for downstream task that it has not been trained upon, you have to remove the top layer of your neural network, add the extra layers for your downstream task for any transfer learning, and then you can train on the downstream task. So a lot of processes are actually involved. So even if you do Keras and TensorFlow, you have to still do a lot, right? So how do we get around that? That comes, there comes Hugging Face, very popular library. They give you APIs for all the popular models. So there's a transformers library which contains all the GPT clip, I think it contains clip too. So all the popular foundation models, the pre-training step, the pre-processing, everything, there's an API. They even give you the actual data which it was trained upon. So you just have to add those lines of code and do the training. That much I think you guys can do. And it's a model hub. So if you're training something new, you can upload it there. People can try it out right there. They provide those functionality. You can download it, make it better. So those things they can do it as well. Tokenizers, again, it's like the pre-processing steps. They give APIs for all the popular models. Going a step back, Hugging Face was mostly, and I think they still do, it was made to train transformers more easily. So I think most of the models, if not all of them, are actually transformer-based models in Hugging Face, which are so popular these days that hardly any other model that is trained which doesn't use transformer paradigm. Accelerated interface, they do a lot of things which can make it your code run really fast in environments with GPU or deployed environments, do a lot of optimizations, quantizations and things like that. They have a big open source community, so you can be part of it. They also do courses in education. Some of my own concepts I've clarified with their how they describe things, and they do it really well. Okay, so I would stop now because my slides are over. So either you guys can ask questions or I'll talk about the last time. Or I don't know if I've run out of time.
Yeah, a couple of minutes, so better maybe questions.
Yeah, let's do questions then. I guess everyone has exhausted the question.
Yeah, with the choice of loss function, is one definition of loss function will serve better than another definition, and will it depend on the use case that we are interested in?
It does depend on the use case, as well as it could be empirically determined. So a lot of times there could be multiple loss functions that seem like they'll do a good job, but with more experience, you would know which one works better than the other. But sometimes you have to try a few and see where most learning is happening. Sometimes you have to modify the loss function and create your for certain use cases. So everything.
Yeah, I have a question from your previous slides. You mentioned about the encoder and decoder, and you said that one is a mirror of the other, just opposite.
Yeah.
And so if I can think that about some function, can I think, if I can think the encoder as a function, so it would be possible to think the decoder as the inverse of that function?
Yeah.
So actually the generalized inverse
it's a good abstraction. Yeah. Yeah, it's an inverse of that function. Yeah. Not always, you can have variations in it, but in the most fundamental way. Applications.
Follow up my question. So in the training process,
yeah,
are the encoder and decoder constrained to be inversal of each other, or can they be like trained differently?
They can be trained differently. They don't have to be inverse of each other. You can use multiple decoders. The most easy way is to just mirror it because you've already implemented the one side, so reversing is perhaps easier. So if you want to do something slightly different, so for example, in the the transformer attention is all you need paper. Their decoder is different from their encoder. It's more or less the same architecture, but it has different elements to it. So it doesn't have to be the same thing. Oh, sorry.
So, is there any advantage to or any use of having different decoders and encoders, or is it just a matter of choice?
Definitely, it's a matter of use case. What could be supported by your data? What kind of architecture? Like what modality? Like is it text? Is it image? Based on that, you'll use. Is it sequence data? So I gave an example of LSTM encoder decoder. Those are good for transformers. Are good for sequence data, but transformers are also not good for image data. Convolutional neural nets are good for image data, so you can use that as encoder decoder. So basically, whatever is the use case, and you can do some experiments, some experience. You can make very complicated structures as well based on your particular use case too. Sure.
In an LSTM model, how does the model decide that these many words will be in the output? The input words you have hidden features and all, but how do you decide that there are these many words that are required? How does it stop?
So with LSTM, you can kind of do maybe an infinite number of sequence because it's just like the same LSTM. You're inputting something, creating a hidden representation or a hidden state, and then feeding again that hidden back into it with the second input. So I in the figure there's like multiple LSTM units, but it's the same unit that kind of goes forward. So you can do it as many times as possible, but in practice, usually people use a fixed number of input size. So input size are usually predefined, fixed.
But so, is there any way to change the output size on the fly?
Yeah, so output size, yeah, it is actually on the fly. So there's I forgot what it's called, but there's a specific word that is, so if the decoder so if you're doing a translation, and if the decoder outputs that particular word, or like a full stop, you know that don't decode anymore, but you can keep doing it. So it is in a way infinite. So with input, you can do any size. With output, you stop whenever that full stop, or I forgot what's the technical name for it, when you encounter that. Until that, you keep producing with the decoder.
So ChatGPT will continue to do things until it receives this particular.
Which is like end of sentence.
Yes. So end of sentence token response. So any other?
Yeah. I had two questions. First, like in the start, you said like we will do the batch learning, and for every batch, we can just take down the loss and do target for the batch. So I'm not able to see what is the motivation behind it, because you can't just go for the whole set.
I mean, if you have that much CPU power, you can do it. But usually the limit is the CPU. And I think something about you also don't want, it's better for not overfitting when you're not showing all the data at once. So it learns different aspects. It doesn't learn about the other thing. And then you adjust the gradient so that if you just show everything at once, there's a possibility that it might start overfitting in the beginning. So maybe is that for that. But one thing is from the application point of view is that you won't be able to fit all that data. Some people do. You can actually do that. Yeah.
And the second question was regarding the tag.
Yeah.
Here, like, when you were keeping the images and the image encoder and text.
Yeah.
Where all of them are distinct, or like sometimes we have got some images and all. How does it, like, if we need it distinct, then how does it deal with the similar one?
Oh, so are you asking for the clip model where I showed the matrix? And so if some image is also related to another caption, which is similar to, So we have the pairs from the beginning, right? Like this image has only this pair, but maybe you're not asking that, but maybe you're asking that, but I think the question might be if there's another image that also matches another caption, but there we are still minimizing that loss, right? We should actually be aware of that relationship, right? And we should not randomly or flatly reduce all the losses only for the diagram. Again, you're right, but we don't have that resolution of training data. So it's shown that in CLIP, even if you do this, because you're doing it at such a large scale, it takes care of that automatically.
So following up on this question, so could you do some sort of a pre-classification on the input data and then maybe assign similar weights to, let's say, all the images that have been assigned to one class and like assign like, let's say, common caption?
You can do that, yeah. So it has been done. So a lot of foundation models, they use other foundation models that have come before them to generate such data artificially or create this, we call it ground truth mining. So yeah, you can totally do that.
When we input these vectors inside, how do we know that they are independent of each other? If they were dependent, we could actually decrease the amount of input data that we find.
I would say a general rule of thumb is more is better. So as long as you're training with a large amount of data, you don't have to care about what is related to what. They might be related to each other, but again, it depends on. So
we cannot save time if we knew the relation between and.
So you're saying if we only get like very good quality of inputs but less data, then it can learn faster?
I'm asking, when we are putting an input vectors,
Yeah.
are they always do they need to be independent of each other? That is.
What do you mean by they're not dependent on each other? What do you mean by dependent on each other?
That is, the variables are not they cannot be formed from each other.
So variable within one vector?
One vector cannot create the other by some transformation.
I mean it can. Yeah.
I think he's
And
asking
it could be
about-
related, but it doesn't hinder any learning. You know, I mean, you wanted to learn those similarities at the end of the day. So, just let me know when you.
Yeah, I think maybe we need to switch. So
Yeah.
What's the time scales? It's a PDF. So all right. So this is the last couple of talks, and we are going to
Maybe
change
still
the.
showing Ashita.
Yeah. Yes. You keep going.
What happened?
No. Participant.
Right. So we'll be changing gears a little bit. We'll be talking a little bit on time series, which is a very important aspect of astronomical data in general, especially modern astronomy. And of course, time series also appear everywhere else in all kinds of spheres. So
So is this going to work with PDF or no? Or can you just? This, okay, yeah, sure. All right. So one of the main things about astronomy in the last couple of decades is how astronomy has been changing in terms of how the data are taken. So here I mentioned a few things. So we went from photographic plates to CCDs. What you see here are two photographic plates taken some time apart. This one was in 1990. This one was in 1992, same part of the sky. And that's the only way we could look for changes. In fact, there was not enough going on in terms of looking for changes, especially across the entire sky. For specific areas, yes, people were looking at variable stars or looking at how supernovae may be found in galaxies, etc. But these two images are from DPOS, the Digitized Palomar Observatory Sky Survey, which went on for 15 years. And it took the survey 15 years to take one image each of the entire northern sky in 3 different filters, which were photographic emulsions at the time. Again, let the numbers sink in that 15 years for one image each in 3 filters. Whereas with ZTF, which is the current survey that we are running from the same telescope, what we can do is that we can do the entire northern sky every 2 to 3 nights. So 15 years to 3 nights. So that's the kind of changes that have come about. And multiple factors have been important in that. One thing is we went from photographic plates to charge coupled devices. So it's all electronic. You don't have to go and process images. So these were 1 hour images, and the same number of photons we can collect now in, or we can get to the same depth in 30 seconds. Again, with the same telescope, same aperture. Right? And that's because there are multiple amplifiers in the CCDs. You can have a large number of these with high resolution there. And then with GPUs, what has happened is that the processing is much faster. So as you collect the data, you can parallelize your inputs, can parallelize your processing and be able to do it really well. And of course, what internet allows you to do is it allows you to transfer the data. So when I started observing long back at Kowloon, we had magnetic tapes, 150 megabyte was the capacity, right? And so you have to go observe it with that and bring it back. And now ZTF observatory, which we have Palomar, every night we take 1.4 terabytes of data. So 150 megabytes was what we had, 1.4 terabytes. And all the data are processed in real time. And there are other surveys like SK India that will be going into much higher things, or even other radio. There's a parallel meeting going on today about radio astronomy. So they are the ones who use a really large volume of data nightly. But one thing that happens with radio astronomy is that you also end up throwing a lot of those data because there's a subset of the data that's really something that you can do for the processing, whereas with digital, astronomers tend to keep it all, sometimes because they don't agree with other astronomers how they reduce the data and they want to do it all over again, but that's a separate story, right? So with something like TESS, for instance, TESS has very large pixels and it takes data in those things, but it can sit on one location for 1 month as the transiting exoplanet observer. And so what you get there is that you get data at resolution of say 2 minutes, or in some small cases even 20 seconds for 1 month long. So those are continuous time series. And with continuous time series, you can do lots and lots of things, but continuous time series or regular time series in astronomy is an anomaly really. Because in most astronomy use cases, what you have is that you go take an observation, take another observation some other time and so on. So you are at the vagaries of weather, then the phase of the moon, plus day and night cycles, and annual cycles when half the time the objects of interest are in the direction of the sun. So it'll be vary of all those things. And these are some numbers from ZTF. This is a much older DR. We have been doing data releases every few months, but you can see how many number of observations that you have with GRI. So, and this is again the entire northern sky, but about 20,000 square degrees or so. And so, but even if you had to take a small portion of the data, then you have got very deep images, corresponding light curves for those. And those are the currency for many different problems that you can handle with various techniques that we have been talking about. So LSTM was mentioned today for time series. So it is better for regular time series, not as good again for the kind of time series that we have here, very irregular ones. So What happens in astronomy is that our data are very gappy because of the reasons that I mentioned, they're irregular, and each point comes with an error bar. And the error bars at different points are different because of, again, how the observing conditions were, what is the depth that's allowed at the time, etc. And so what happens is that there are many methods that people end up using that ignore the errors sometimes, which is not the best that you should be doing, but that may be the best that you can do under certain circumstances. So this is a typical time series that you can see. And so these gaps are the annual gaps when you cannot observe that object. And these triangles are the upper limits. What that means is that you know that the object was there, you don't see it. But then based on other objects that you can see that if the object existed, it was at most as bright as this, but likely fainter. So because the way astronomical time series are, 18.5 magnitude is a brighter magnitude than 22. So this is brightness is increasing that way. And for those of you who are not into astronomy, the naked eye at a dark spot can look at stars, or the stars that you can see are from roughly 0 to 5 magnitudes. And 5 magnitudes is a factor of 100 in brightness. So when we talk of 5th magnitude star, it's the faintest that you can see roughly at a dark spot. So 20 magnitude is 15 magnitudes fainter, and every 5 magnitudes is 100 times. So this means it's a million times fainter. So these numbers are about a million times fainter than what we can see with your naked eye. And that's the dynamic range of a few magnitudes that we have with a telescope like ZPF.
Sir, I
Yeah.
have a small question.
Sure.
So can go back to the previous slide. So I need to see or find out the gaps between the data, the irregular pattern, and the heteroscedastic nature of the data. So, sir, is it not necessary to find out multicollinearity?
So there's a lot of those things that happen, and some of the inputs you already know when the data have been observed. Not just that, because generally you have a CCD which has a large area. For one object, you know these times, and you also know that the other objects in the same CCD image are at the same time also. So there are many correlations that you can find out with that, and the upper limits, that's how they come about. So I know that was the faintest object that I've seen. So many basic correlations have been used, many basic statistical methodology have been used for that. All right, so here I wanted to show you one specific example that this is the time series that we have. Again, this is magnitude on the y-axis and time on the x-axis in days. And then if you look at a small portion, you can see how the variations could be seen if you had continuous observation. These observations were not continuous. But then in general, what you can have is that if this is your time series, and if you were to zoom in on a small portion, and for the same object, small portions can look different. For most stars that you can see in the night sky, about 80 to 90% don't vary much in our lifetimes. So it's the small number that we are talking about, but the small numbers themselves, when you're an astronomical number scheme, they can be very large. So for instance, in ZTF, we have a couple of billion objects, and 10% of that is 200 million, right? So that's the kind of things that one is looking at. And when you have large sky survey, then you can find many, many pathological examples of these kinds. So one thing that you do, because these time series have not only different gaps, but also the number of points in different light curves, these are called light curves, astronomical time series, they can be different. So you cannot do a one-to-one comparison easily. So what you end up doing is to try to change that dimensionality of 100, 200 into say 50, same number of features that you can calculate into. So here are a few, you can find out the amplitude of a given light curve. What is the difference between the brightest and the faintest source? What is, how many objects, how many points are beyond one standard deviation and so on. So each of this then becomes a dimension. So you're converting your 200, 300, 1,000 number of points in your time series into say 50 numbers or 100 numbers. And this is still a high dimensionality. But in that high dimensionality, at least what you can say is that all time series, all objects are on par with each other because each of them represent a point in this high dimensional space now. And you can start doing various comparisons with that, etc.
So, do these features have to be physically motivated, or
it is best if they are, because that way you can easily correspond what you have in your mind when you see something, when you see their distributions. But the beauty with newer techniques like deep learning and so on is that deep learning allows you to go in a very high dimensional space. So you don't have to be restricted to these say 50 dimensions. You can think about 1 million dimensions that you can go into, and then you can, the technique can find out which 10 are the best for you. So there's a lot of dimensionality reduction that happens. So traditionally, as things have grown, they were all motivated with specific physics, motivated with certain correlations in mind. But now people can be more adventurous and either design a large number of features or let the techniques design the features and figure out how the relationships between those are. And so this is how things can look. So this is your input data here, right? And then if you start designing or defining tens of features, then you see that it's all blurred there, because not all of those are independent from each other. So when I talk of high dimensional space like 50, 100, it's not a real 50 to 100 dimensional space which is orthogonal, all the dimensions and so on, right? It's just 50 to 100 handles that we have, and the real dimensionality may be 5 or 10 perhaps, or even smaller, right? And that's where we need to go. That's where we need to go and find where they lie, etc. So there are something that you can define if you're looking at pairwise observations in two filters. You've got a bunch of Welch stats and statistics. So this is the I statistic, the J statistics, K statistics, L statistics, and so on. And these are again statistical things that these take into consideration. And this is just one example. The features that we saw were many, many different ones, and starting from very simple ones to something that's fairly complicated and so on. But then what you do is that's what you start with and go into dimensionality reduction with those, and so essentially these are the kinds of time series that you have, which you convert into a single point in this high dimensional space, and then there you can start saying certain correlations and certain clusters and maybe certain outliers and so on, and those are the ones that you'll be going after.
So the main objective is classification, not a
classification is one of the objectives, yes, but there can be anomaly detection.
And
there can be similarity finding. For instance, I may have a couple of very unique kinds of objects that I found, and I have got 1 billion time series. I can ask myself, are there other examples of this kind?
So are we going for prediction modeling and using this?
Prediction is also an important thing. So all those things are there. So I'm not defining any specific problem as yet, right? I'm simply presenting what is out there. And then it's for us to define any projects or problems that we may have, etc. So here is an example where how one could use multiple filters to do that. So you have data in G filter, your data in R filter, they may not be simultaneous, so you don't have a color of the object. Color is an important term in astronomy, which essentially tells you of the ratio of brightness in two different parts of the electromagnetic spectrum. That tells you about what elements may exist in that source, what is the temperature of that source, and so on. But because we may not be able to use the same telescope with two different filters at the same time, you have observation in G at one point and R in another point. So how do you make sense of that? So you can use something like the LSTM, which was mentioned earlier, to try to combine these data sets in a meaningful way. So it may involve some kind of interpolation or use of Gaussian processes to figure out how to impute the data, etc. Again, we won't be able to go into details of these. So this is not now. Click. Yeah, it does. And what has been happening is that there are many other things like transformers and so on have been seeping into time series data for astronomy also. So here you can see a raw time series, and if you fit it with the Gaussian process, how it looks, and then you can take GP mean and try to figure out various embeddings for that and try to go into all the kinds of different problems that were mentioned earlier. So you could do classifications, similarity searches, clustering. Clustering would be the typical one if you don't know what the classes are, etc. And then one thing that we designed, for instance, is that, so this was when CNNs were around and many of the recent generative techniques were not in vogue yet. So we decided to convert our time series into images and use the images with CNNs. So CNN was like a hammer at that time, and we said, why not convert whatever we have into a name and use it with that? So what we did was, if this is your time series, take every pair of points. Here you've got a delta T and corresponding delta M. So you create a 2D area where your x-axis are delta T's and y-axis are delta M. So small delta M's, because there'll be many observations which don't change in brightness at all. So for every pair of points now, you have a point that comes and sits in this figure, in this 2D image. And so if you've got n points in your light curve, you have roughly n square points here. And now you can get a density. And that density is what is here. Then you can do various kinds of normalization and so on. And this can be a fairly small thing, just like The MNIST data is fairly small, 28 by 28. We had images that were roughly the same dimension, so we could use various models that existed. And so from each individual light curve, you get an image like that, and you can go and start classifying those things. So this is, we had various variables from CRTS data, and those we were able to classify. They start looking different. So again, with different cadences, with different filters, you may have to make slight changes into the kind of grid that you need here. So some domain-specific inputs may have to go to that, but once that happens, you can have it. And then, just like Cliff was mentioned earlier, here again, what one can do is that you can take time series data and some other labels and do multiple encodings and try to start it. This hasn't happened yet. Recently, I heard that there is a group that's starting to work on something called AstroClip, and I haven't looked whether it's exactly this that they're doing or somewhat different. But those ideas are out there now, and many groups are going to doing things related to that. So I will finish with this. Recent approaches have included Gaussian processes, transformers, and also there have been a couple of foundation models. So IBM is coming up with a foundation model. Caltech is coming up with a foundation model for time series. And those are more versatile, but again, may not be very easy to use on astronomy data for the reasons that I mentioned. So these problems still remain. Accurate, fast period finding is the challenge. So what do we mean by period finding? Most of the variables that you see are periodic for some reason. These may be binaries that are going around each other with a certain period, or these may be pulsating objects that have a certain period. And given these very sporadic data that we have, figuring out what the period is a non-trivial thing. So one example that I like to give is that if you are out on a safari, you go to a national park, say Tadoba, and you want to look at tigers. So what you're doing is that continuously you are looking for tigers everywhere in your surrounding area. But instead of that, if you are keeping your eyes closed for 5 minutes and opening it for half a second, and again keeping them closed for 5 minutes and opening it for half a second, and looking at random directions, right? You're less likely to see the tigers. We are exactly in that time frame, in that frame in astronomy, and that's the kind of data that we are trying to use. This period finding in particular will be more critical with that. And then there's also the characterizing using few points is non-trivial. So there was a challenge that was run by the plastic group for supernova and other classification. So they gave these time series and asked people to classify them. There were two problems. One was classify those. The second problem was use only the first 6 points and see if you can classify. Not a single group even attempted that. Things have changed. Again, that was a few years back. Now there are better methods which you can. There was a recent paper which also talks about being able to say which is the brightest point and the starting point of transient based on very little data. They have used LSTMs and RNNs to train and so on. And again, forecasting is important. So earlier question that was asked is that's going to be something that's going to be quite critical. So I will stop with the time series part for now and go on to the last part. But before that, if there are a question or two, we can take those maybe.
The last period sampling is quite low compared to the
Okay. That's where the LLM should really come in. So I didn't mean fast period as in short period, but doing it quickly.
finding
Fast finding.
So that maybe you can switch to the next one meanwhile while there's another question you can check. Any other question before we switch?
light curves that you're converting into images.
Sorry?
These light curves that you're converting them into images. Do they need to be? Are there any conditions on these light curves, or they can be done for any light?
No, you can do it for anything. So even if you had 2 points, for instance, right, they would have 1 dt and 1 dm. So it will become 1 point somewhere in that image. And everything else will be 0, that will be 1, depending on how you're normalizing it. All right, so what I'm going to do in this last part now, we have got about 15 plus minutes, is talk a little bit about best practices in general related to programming, and the other part is about reproducibility and interpretability. So something that comes right at the start of everything and something that at least should come at the end of everything. All right, so this is roughly the outline that I have. Best practices for programming in general, what are the required ingredients for any project, a bit about interpretability, explanatory, etc. Now talking a little bit about bias maybe. So whenever you start a project, before you start a project, what you should really be doing is dig for requirements, try to figure out what the project is about, document the requirements right at the start. That is something that most people don't do. They try to document later on. So what maybe. Then make use case diagrams, maintain a glossary, and again, document. That's really very important. And when you are at a point where you want to modify something, the modification cycle should again start with writing tests. Many people don't do that, but you should really do that. And now, especially with large language models and code generators, writing tests is really easy. So there's no reason not to do that. So write tests, make sure that the tests fail. Why is that? Because then that becomes a good test. So you go and modify it after the test has failed, then change and compile, and now make sure that things are running fine, right? Otherwise, your test is not going to be a great test. So, and then of course, check in your code, use things like GitHub or whatever else you are using with that. Validation is also very important, that you should not trust the work of others. And when I say you should not trust the work of others, I also mean you should not trust your own work. So when you write code, you should run the validation test and have that part of yourself. So validate data like numbers, characters, etc. Put various constraints, like if you're using declination in astronomy, it better not go beyond -90 or 90, right? And check for consistency again in various different ways. Then when it comes to code, don't try to optimize your code, try to benchmark it, try to figure out where things are, how things are. Don't optimize data structure, measure them, how much data have been taken, how fast you can put them together, and various different kinds of things. Cache data whenever you can, using things like memorization and so on. Otherwise, you are going to be generating the same data again and again. Then you should also benchmark caching strategies. So it's not always the same caching strategy that may work for everything. And this is especially true when you have large data sets, right? And then don't optimize applications, but profile them. So try to figure out where different parts of the program are taking up all the time that they have. And then these are three very critical things that you should keep in mind for your data. Make sure that you are not duplicating code. You shouldn't be writing the same piece of code in two different functions. If you see that it becomes that's what you're doing, then you may want to separate them into two functions and call one from the other. Again, in some cases, you don't want to be calling millions of functions. So very small piece, very specific things, that's generally fine. Orthogonality, make your functions programs orthogonal so that one piece of code should be doing just one thing rather than doing a whole set of things within that. And refactoring is quite important. So many times you write code in cowboy mode, put it together, but then you should revisit it, make sure that you come back and make all the earlier things that were mentioned in that. So make sure that there are no duplications, make sure that they're orthogonal and so on. Also try to design by contract. This came up in 1997 from these people I admire, that you should, for each of your function, there should be preconditions. You should say, what is it that this function is going to do? And then there is post condition. So once that function has run, what is it that you should do? Where you should end up? And what are the class invariants? What are the things that are not going to change? So in general, you should be lazy. It should do the minimal number of things, any function. Be strict in what you accept, promise as little as possible, and be lazy in general. And that's what is then going to give you the inheritance and polymorphism that we talked about earlier. And then if you find bugs, and there will be bugs, what should you do? You should check boundary conditions. Why did it come about? And describe the problem to someone else. This may sound like a psychiatrist, but it helps. When you describe it to someone else, you realize, oh, maybe this is not it. This is what it is. So please do that. And then ask yourself, why wasn't it caught before? What is the condition that came up now that led to that? And then that also tells you, could it be lurking somewhere else? Maybe you should look for it. And again, that tells you about orthogonality. Because if it is lurking somewhere else, then that means your code was not orthogonal. Make sure you do refactoring and go and do that. And then you should ask, you already test, right? If the tests have run fine, are the tests bad? You should be checking for that. And in general, you should do portfolio building. There's a wide variety of things that you could be doing. This particular slide is slightly old, so it may have things that you have not heard about and so on. But so there's something called a shell, for instance. And you haven't heard of it. So in general, this is about portfolio building. So be very wide. Know a couple of different kinds of languages, not a couple of different languages, but kinds of languages. For instance, something like Ruby, maybe, right? Or Julia is a fantastic thing. Julia is as fast as C and as versatile as Python. It doesn't have as many libraries yet as Python, but that's something that we want to look at. Or things like Flutter and Kotlin and so on, right? Various different things. So text manipulation, that's very important. So even if you don't do that too much and there's LLMs and ChatGPT, you should know how sed works, how awk works. Those are the very basic Unix building blocks, and spend maybe half a day working about that. So in general, the lessons about how you should work with your programs and so on. The chain is as weak as its weakest link, so you should make sure that weaknesses are covered. You should have lots and lots of comments in your code, lots of tests. Again, I keep on saying this, but orthogonality, don't duplicate, design the contract, and know the features of whatever you are using. So the better you know any system that you are using, for instance, if you are using visual code, you should know the ins and outs as much as possible of that. Or if you are still using VI or even VI, you should know what is it that you should best be using, or Emacs or whatever editors that you're using and so on. Any questions up to here? That's something that I like to show, that every program can be optimized to be smaller, and there's always one more bug. So every program can be reduced to one line bug. That's something I should get into. So we'll go on to the interpretability part, but before that, if there are any questions, maybe we can quickly. All right, we can continue that during lunch or whenever if you have them later. But going into interpretability, for instance, what's happening with these bigger and bigger models is that there's a danger that some of them are too black boxy. So they always produce answers, right? And if you have no way of knowing how good the answer is, many times people can simply take the answers and use those in the papers and be done with it. Which is not the right thing to do, right? So you want the models to be interpretable or explainable. So interpretable models will be where they come with what they are doing. So they tell you as they do why they are doing something. Whereas with explainability, what happens is that it's generally post hoc explainability. So the model runs, and then there are ways to be able to say what the explainability is. And so there are a few different ways that you can do. So these things that I've shown here, AB, ACB, and so on. So those say that where these things can be sitting. So Ajit showed one example where he showed how you can visualize different parts of a model. So you can do that right at your inputs, the intermediate levels, or at the outputs. So you can be looking at all of them. So there's activation maximization, where you look at initial layer filters, very easy to visualize, or saliency maps, look at various kinds of gradients or understanding attention of the classifier, where it is paying more attention, etc. Or class activation maps in general. So here's a broad, one part is missing, but that's all right, I guess. So what you have is that interpretability methods, you can have local versus global methods. What is the purpose of interpretability that we have, or you have got model specific versus agnostic mode. And then depending on data type, you can have different methods. But in many of these things, the reason to do interpretability is to have fairness and trust. You should be able to trust your models, and others should be able to trust your models, and the model should be fair in general, how you get to that. And fairness in this case is also about various biases. So for instance, there have been various models in which, depending on the data, they were good at classifying something, but horrible at classifying, or even understanding something in a completely different way. So SAM that was mentioned by Asilan, the segment editing model, you should look up that paper. It's a model in how to write a paper, keeping in mind how biases have to be mentioned, how you do various things related. They also have model cards with them and so on. So some of the things that they did, for instance, is that they had a total of 10,000 images or 1 million images, 10 million images actually. 10 million images, and they had 100 masks per image on average. So they had a set of 1 billion masks. And what they did within that is that they looked at the clothing that people were wearing in the images, and they did an analysis as to whether their program does worse if the clothing is of people who come from poorer countries or the clothes are cheaper. So even that kind of bias is important. Otherwise, what's going to happen is that you generate a model that works most for, say, the Western countries, and it's going to be horrible for some other countries. So trying to understand what kind of numbers or what kind of parameters go into it is critical, and be able to see that in different ways. And then there are various methods that people have been using, and there have been additional newer methods to Sublime, which is local interpretable model agnostic explanation, or Shapley additive explanations, etc. So lots and lots of different things are coming up. Again, we don't have too much time to go into that. Here's an example for the DMDT that I mentioned earlier. That was where we went from the time series to images. And here we found something quite interesting. So the attention was being paid to areas which did not have anything. So it was essentially looking at boundaries and outside, and we haven't gone into details about trying to fully understand that yet. We've been designing experiments for that. Or attention was many times paid to longer durations rather than shorter durations, even though the periodicity was shorter. So these are the kinds of surprises that come up when you try to look for something rather than simply push something out that you may have. Or saliency also indicated somewhat similar for different classes, where the model was paying attention, etc. Here's an example with which I would like to finish this with the gravitational wave data that we have been doing. So LIGO puts out these gravitational wave alerts, and then because, especially if these involve neutron stars, then many telescopes quickly move there to try to see if they can find a counterpart. That's something that's a hot area right now. And what has happened though is that some of these alerts were related to objects that didn't exist. So LIGO retracted them. So what some of us did is that we took the public data that's out there, and using only the public data, we wrote a classifier which could say whether the alert is likely to be true or it is something that's unlikely to be a real one. So what we did is that this is the sky map that you get. And then because, again, we wanted to use CNNs, which are far better with rectangular images, we reprojected it into rectangles. And in addition to this, there are things that are available in terms of which detectors the data came from, and there were things related to volume, distances, etc. So those formed other parts of our network. So we had a convolutional part, we had a DNN part, and then we combined the two parts. And that is what we got into the GW Skynet. And Skynet has been working quite well. But then what we did is that the first one was only real or bogus, which was great. Then we said, why not go into GW Skynet Multi, where we said, once you determine whether something is real or not, then if it is real, then try to see whether there's a black hole involved or there is one neutron star involved or both neutron stars involved. And there we ran into a very interesting problem that we could do a glitch versus all classifier, and all these are binary classifiers that we have. And a neutron star versus all, let's say whether there is a neutron star or a black hole, whether both are black holes. And here, for instance, we were not able to separate objects when we could not tell apart if there was a single neutron star or two neutron stars. There the accuracy was really low. But it was good enough because if we had a neutron star, then there was a likelihood of there being a counterpart. So we were able to go to that. And then even this classifier was great. So we went ahead and published it. But we were still wondering, even to ourselves, that is it finding correlations or is that something real? So let me go back to the encoder decoder that was mentioned earlier. So the encoder brings down something to a vector, a small set of numbers, and then the decoder tries to bring it back. You do loss functions and so on. So there were examples in COVID, for instance, where people were trying to do all kinds of classifiers, and there was one classifier that was fantastic. It was being able to say whether someone had COVID or not really easily. And it turned out that the images that they were using as input, on the top right corner, there was some indicator whether there was COVID. So what you have is that you can reduce the entire image, a large, say, 10 megapixel image, into a single number, right? That's your vector that says, is there something there? Yes, then it's COVID. It's as simple as that. We don't want that to happen. So we want to really understand what is happening. So even if this was working well, we started asking ourselves, are there correlations or not here? Or what is it that it's linked to? And so we built a whole set of examples related to how things will be. So these are a bunch of things that were mentioned today, right? And so we didn't really go into things like as simple as decision trees. Hopefully you have heard of that. But this is an axis where how is it good for human understandability? In decision trees, it's really easy to understand, right? You're making decisions of very specific things. Is this mango sweet or not sweet? Does it come from India or somewhere outside and so on? It's really binary. You can go on doing that. They're very, very interpretable. And then as you go here, they're less and less interpretable or understandable for humans. And this is where the high dimensional, highly non-linear method come in, deep learning methods. Even the random forests are way down here compared to that. And there are future explanation models or methods which will push us towards that. In general, the hope is that we'll go in this direction where human understanding is also high, but the model complexity is also high. Model complexity in the sense that it can handle more questions, handle more problems, and that's where we want to be able to go. And that's what we really want to be doing. And so the number of things that we can be doing right now is still few. We are not there where we can really go into the direction, but that's what we can try to keep attending. So here what we did is that we did many perturbation studies. So perturb the inputs in the sample. So you can change. These are the typical sky maps that we had. So we said that if we leave everything else and say that this actually is much smaller area, go here, for instance, 1/4 the area, or go 4 times the area, or completely scramble it, and not change anything else, then what are the outputs that we're going to get? And we use those things for various things. So that was one example, but we had many more quantitative things like quantify effects on the output score of each binary model or population study levels, etc. So these are the kinds of things that we started saying. So we have got for glitch sources, how they look for neutron star sources, for black hole sources, etc. So these are the kinds of interpretability studies, explainability studies that we can start doing for most of your models. And as we did, sometimes you may be forced to do it post hoc, but if you can do it right at the start, and that is where the requirements part that I mentioned comes in, that will be really, really good. And so here are other things about the coherence factors that we had for the same problem, how they change from glitch to source, etc. And that gave us very good insights into whatever our model was made. Okay, I'm going to stop with this. I will mention biases and with my summary slide. So Ashish talked about LLMs and a little bit about their hallucination, but there's much more you should be wary of that, what can happen with that. I think it would have been with the RAG model that he had a slide on where we could have gone more into that. We are doing a little bit on biomarkers together on that. So hallucinations again come from the fact that these models are always going to give you an answer, right? And then because their English is great, they're going to sound confident like Americans, right? I'm an American. But all models are limited by their input. So you have to be wary of that again. And so whatever inputs have gone in, again, going back to the SAM example that I mentioned, is important. Perturbations allow us in a limited way to overcome them, but that is not sufficient. So we should also be looking at various things like edge cases and anomalies and so on. And then finally, I'll stop with that robustness of programs is critical for reproducibility. Important to convert black boxes to be more transparent in whatever you do. Use tools like generative models, LLMs, and other foundation models extensively, but be wary of their biases and so on. And in the next 2 days, what we're going to do is that you'll see a lot of use cases in astronomy. So that's where hopefully you keep many of these things in mind. And then when we talk of possible projects to do together on various data sets and techniques, we can keep on bringing these back and so on. So I will stop with that and happy to take any questions before we break for lunch.
Questions? Yeah. So when you were analyzing the gravitational data, were you using only the sky localization?
No. So we had the other things also. For instance, there were a set of detectors we had. So we would blank out one detector and see what changes that we do. What we don't have is a single detector output because that is not easy to analyze, right? Because you don't have corresponding data from any other source. But yes, we changed the other things as well. These are more visually appealing, right? Yeah. So it's easy to show.
The reason I asked when I was wondering, like, using only the sky localization, how could you differentiate between different, let's say?
No, that's not interesting.
So you talked about the robustness of programs, and as you said, machine learning models are basically trained always to give you an answer. But how do are there training methods where we can train the machine learning code to say I don't know when it is not sure, and how do we prevent catastrophic confidence?
Right. So there are things that are built in that way, right? Because when you have something like a classifier that goes from 0 to 1, then you do have defined thresholds where you say that, okay, so like star galaxy classification was mentioned earlier. So you typically would have a curve that is U-shaped. So on this side you have got stars, on this side you have galaxies. And there'll be a thin thing here. Ideally, there would be a delta function here and delta function here. But generally you would have this shallow valley. And this is the region where you can say between these two, whatever is there, it's ambiguous. And the model is saying that I don't know. And so many people, even in papers, what you have is a binary output. It is this or not. That's not a good thing. It's always a good idea to carry these confidences that you get and then allow people to put their own thresholds. So some people may be happy to put a threshold at 0.7 and be done. Some may want to put. So that's where the things about whether you are okay with false positives or false negatives comes in. Right. In case of astronomy, for instance, like LIGO, if you don't want to waste your time taking data, then you want to try to be sure that you have as many real LIGO events as possible. Whereas what may happen in other cases is that it's okay, I have a lot of telescope time, I can invest more time taking observations of everything, but I don't want to miss any. So that is where the limit will be, and that is where people will have to decide based on their own experience, based on their own resources, where the threshold should be.
But also, like, the probabilities could be wrong, so it could catastrophically think that something is a star when it is.
Yes, but again, that depends on the data, then, right? We input data, and then it becomes even stronger in case of something like detection of cancer, where both Astronomy and I are working, and if you find something that seems like cancer, whether the doctor should tell the patient or not, because if there's a 90% chance that it's not cancer, but what about the 10% chance that it is? And that's where, so we have been working on early detection, and it's important to do the detection early, but at the same time, one should also understand that many of the early detections are benign and nothing may happen for 10 years, 15 years. What do you do with that? And then you don't want to be too aggressive. So those questions are very important. And again, better data and trying to bring diverse set of data is going to help with it. So you have your some set of data that tells you something, and then you bring other kind of data, other modality of data, then that gives you better insights into that.
Yeah. So I'm a bit intrigued by the fact that you said that you should profile your programs but not optimize them. So what was the motivation there?
So the motivation was that sometimes what happens is that you could keep on optimizing for really silly things, right? Something that is not really taking much time. You want to make it more beautiful. You want to make it into a gem, the program and so on. But there's some part that is really taking most time, and you're not. You suppose you may not even be able to do anything about it. For instance, if it involves downloading data from some remote area. So to that extent, I meant that you should profile it. You should make sure that where it is spending the time, and then you may want to optimize the part where it is spending more time.
So just do
but you cannot do that before profiling.
Correct. Okay.
There are libraries also that can be used.
Yes, absolutely. And again, use things like ChatGPT more and more. Be sure that you should know the answer before you use their answer.
Yes.
Right? So long as you keep that in mind, you generally be fine.
Any other questions? Yes.
You mentioned somewhere about caching. That it will show memories.
Yeah.
I know that as something.
No, memoization is a technique. So for instance, I even had a small line there about factorial. So if you're trying to write a program about factorial, right? If you want to calculate factorial of 10, it's of course, so factorial of 10 is 10 times 9 times 8 and so on. But then after calculating factorial of 10, immediately I ask you what is the factorial of 11. You're going to recompute everything. If you have memoized the factorial of 10, then you can simply say 11 times that answer, you get your answer. So that's what.
So here you mentioned that black box is to be more transparent. Can we here go one step further, saying that I have an input and output, I want to understand what's the relation. So can you open the black box and understand some fundamental, is there any law that we can get?
Yes, and there have been attempts to do that. There have been various things about symbolic regression, etc. People have been doing a lot related to that, trying to discover laws of physics itself using these large methods. So yes, short answer.
Okay, so I guess we can stop here. It was a very productive morning session. For all the participants. So IUCAA people know that they have to go to Chittaranjan, so you just have to follow us. Thank you so much. Okay, please, IUCAA people go slowly so that people can follow it.
That was request.